So I'll be discussing the big jump principle and how do you apply it to evaluate extreme events, rare events in certain stochastic processes and deterministic processes. The main work was done here with Alessandro Vesani and Raffaella Burioni, and we have a recent archive paper. But some elements of this talk were considered previously, especially I'll discuss the PhD work of Adi Rebenstock. So let us just start with some kind of motivation. Let us look for one example, and there are actually many examples for what I'm going to discuss, as you will soon see. So I'm going to consider here Lorentz gas. These are scatterers that are arranged in two-dimensional cubic lattice, and the paths are totally deterministic between collision events, and you have these elastic collisions. And once in a while, you can see these long paths along these corridors. These corridors are called infinite horizon corridors. It's very important that the particle can go infinitely either to the x or to the y direction like this. When you look at the individual trajectory of the particle, you see that you have many small events, many jumps, many small collisions, and once in a while, you'll see one big jump. This is the big jump that you can see with your eye here in this particular example. Now, just by looking at this picture, several questions can arise. First of all is the following question. Is this process actually a kind of diffusive process? If you look at these parts, you might say a lot of collisions, so it's more or less diffusive. On the other hand, if you look at the big jump, it's more or less ballistic. So this type of system, which is maybe the most basic model of transport, actually contains in it both ballistic elements, these long flights, and diffusive-like motion. And the transport here is a mixture of both, as I will show you soon. And we would like to quantify especially how these big jumps are influencing the rare events. The rare events will be in the final position of the particle in this model. So if you look at the density of these particles in this very simple model, what you will see is the following cross shape. This cross is related to the symmetry of the lattice. What people know and what most people will focus about is this little chupchik up here, which is the diffusive element of this process. Here, everything is Gaussian. Mathematicians worked a lot about this. The rare events are these, actually these are Paolo tails that you see here along the open channels. And what we would like to focus on is not exactly, this model I'll come back to in the end, but in a simplified model of a Levy walk, we would like to focus on these rare events, which go, of course, beyond the central part, which is diffusive and central limit-like theorem. And out here, the big jump principle will work. And intuitively, even you can understand it. If to reach somewhere here, you need one big jump to reach the end of the motion, because the velocity here is v. So there's no particles beyond this square, because simply the maximum the velocity is fixed, right? So you have a strong cutoff. So all these rare events, roughly speaking, is what is interested in my group. In this talk, I do not have time to discuss this in particular, but we will discuss related processes. Now, one question is, how do you quantify this? Of course, you can simply plot the PDF and look at these tails. But a long time ago, it was suggested to look at the rare events through the observation of the moments. And we look at the moments of the process to the power q. Usually in the usual diffusion, we take q as 2, but that is only because Gaussian diffusion is important. But generally, we have any q from 0 to infinity. Strong anomalous diffusion, a term given by Vulpiani, says the following. If you have in the long time limit some function q times some nu of q, and nu of q is not a constant, we will call this strong anomalous diffusion. Now, if usual Brownian motion, this function will be just simply half. What does this mean if you have here this function is not a constant? It means that you do not have monoscaling in the system. It means that the density of particles cannot scale with one typical scale. In Brownian motion, again, you do have a scaling, and it's simply given by a Gaussian, and u is equal half, and you are done. But generally speaking, you have a spectrum of exponents. A very important observation was made by Vulpiani roughly 20 years ago. And he noticed the following, that in some systems that are, one of them is the Lorentz gas, but there are many systems, I believe, this function q nu q exhibits a bilinear behavior. It's super important for this talk that you have two linear behaviors, because two linear behaviors essentially means that you have two scalings. This is related to the picture I had before. One is diffusive scaling, and one is ballistic scaling. How do you see this from this type of plot? Here we are talking about the low order moments. For example, normalization is q equals 0, q equals 2, this is the MSD. You see this slope here is half. This is like diffusive more or less. So what happens here is the following. The typical fluctuations are described by kind of diffusive laws. Sorry. While the... so low order moments which are sensitive to the center, to the bulk fluctuations, and here much is known. This is essentially the Gaussian or some central limit theorem or some generalization of the typical fluctuations. They have one scaling law, and then you have another typical length scale, and here in this example it's ballistic, so the curve here is 2. So our question is, how do you essentially describe the statistics that leads to these rare events? The large Q is rare events because the larger Q is you go more to the tail of the distribution. And our claim will be that here you have this single big jump approximation works well. This principle will work well. It will be describing the rare events. So this phenomena is very widespread, this bilinearity, and it was started by the group of Vulpiani, but many people, especially actually in Italy, used it in deterministic transport, for example, in the Lorentz gas, Artuso, Ruffo. Again, more importantly, or recently, it was investigated in the context of cold atoms in optical lattices. So there are many, many works on this. I'm not going to go in all the details. Maybe most important, if you want to get some funding for your work, it's found in active transport in living cells. So if you take a molecule in the cell and it's active, driven by ATP, it will show this bilinear behavior. And this was shown by Weiss from the Technion, and it's also found in many body systems in heat spreading FPU. So this is a widespread behavior, this bilinear behavior, and we understand that the high order moments are controlled by rare events more or less intuitively. So what is the outline of my talk? I'll first discuss the single big jump principle, then I'll discuss a model which we can exactly solve, the Levy walk, then I'll discuss Levy gas, and then most likely I will not have time to continue with many other models. So what is the big jump principle? It was defined in mathematics in the following way. Let us consider independent identically distributed random variables, x1 till xn, and they have a common PDF, which is a fat-tailed distribution with some alpha. Alpha can be anything bigger than 0. Then I look at the sum of these random variables, and I ask what is the probability that they are bigger than x. And then I look not on the sum, but I look at the maximum of this list. So one guy is the biggest guy, and you have one maximum. The principle of big jump says that this distribution, this probability and this distribution is the same when x is large. So what does it mean? Instead of summing many random variables, one of them is dominating the sequence. In this context of IID random variables, it simply means that this guy is described actually by, for example, by Levy's central limit theorem, and this guy is described by extreme value statistics. So the tail of Levy distribution and the tail of Fréchet is the same. So if Levy met Fréchet in a pub in Paris, they would compare their tails. It's exactly the same. And this is exactly given by, in this case, it's given this by simple power law. It's super simple to prove this. And this is these two things. However, what was done here was essentially saying, well, this is not only in the limit of large n. This is not only in the limit where Levy works. It's even in the limit for any alpha this works. And you have this thing. Now, what are the type of questions we are interested in? Is the first question, is this principle valid beyond the IID case? If you have some sort of correlation, some sort of disorder, how do we define at all this principle? What is the biggest jump? For example, if we have Langevin pass, how do you define what is the biggest jump, etc.? And then we will show that the principle is working more than you expect from the IID case, but if it is valid, then how do you make predictions with it? How can you use it as an approximation to make predictions? And very generally, in all the examples we worked on, in spreading phenomena, when you have the probability of the sum, you don't have this power law. For example, for the Lorentz gas, you have some cutoff. So you never see this. So the IID case is too simplified simply because you have finite velocities in spreading velocity. So we will find phenomena much more complicated than the IID case. So this is obvious. But still, the principle will work in some way. So how do we progress? We start with a correlation plot. You simply plot the biggest jump and the total displacement in the model of Levy-Walks. We'll do this soon. Then what we do, we calculate the distribution of the largest jumps. So this is like extreme value problem. Then we calculate the distribution of the position of the walker at its very rare events. Then we compare the two. Then we can prove that the principle works for some model. We need to do these two calculations. And this we do the same way, either numerically or semi-analytical for other models, like laser cooling model, laser Levy glass, correlated Levy-Walks. A lot of work we have in this ConMat paper, but I will just focus on the simplest one due to time constraints. So let us discuss the Levy-Walk model. You have here pairs of ID random variables. These are waiting time between collision events and velocities VIs. And you have two distributions, one of them describing the distribution of time between collisions, psi of tau, and one of them is f of v. And then there is a constraint, similar to what Claude Godrèche was speaking, some constraint on the total time. That is, the sum of the times between collision events is plus the last time between the last collision and the final observation time t, which is denoted here by t star. All this sum has to be the total measurement time. N here will be random because in some sequence you have many collisions, some seconds you have other collisions because you have these random, you have this psi of t with which you generate the waiting time distributions. The position is again a sum of random variables. The chi I is simply the velocity times tau I, and then you have the last jump that you perform in the last sequence. This is essentially the definition of the model. It's very simple. If tau would be Poissonian, this would be essentially Drude model. But what we are interested is in a case where the waiting time PDF is a fat tail distribution, and I will consider the case where alpha here is between 1 and 2, which means that the finite, there is a first moment for between turning events, between renewals, but the variance of the waiting time is infinite. For the Lorentz gas with this infinite horizon, it was shown previously that you have psi of tau, tau to the minus 3. That will be a special case because it's actually a transition between Levy and Gauss, and it's very special. But we will discuss this case because it's easier. So the model, just to repeat, is simply you have a velocity, let's say plus 1, minus 1, and you have these waiting times which are power law distributed. And of course, I think all of you know Levy-Walks have been found in many systems, from Lorentz gas to the active transport in the cell. So this is a very well-known and well-investigated. The typical fluctuations are well investigated for a long time. So let us see the big jump at work. So what you do, you simply plot, you take many paths and you look at the biggest jump, and you also look at the total displacement. And then you plot a correlation plot. This is the absolute value of the total displacement versus the biggest jump. And you plot it and you see it goes for large displacement, it's falling here on a straight line. This is an indication that the principle is working. The biggest jump is controlling the biggest fluctuation. And what does the principle stay? This is what we actually want to prove, that the displacement is actually when the displacement is large, is the velocity, which could be a random variable, times the maximum of this tau 1, all this sequence up till tau star. So what we need to do is calculate the distribution of this guy, calculate the distribution of this guy, and then we'll prove that this statement is correct. I'm telling you it is correct. Yeah. Why do you separate tau star from the others? Because when I draw the random variables, I have waiting time PDF psi tau 1, psi tau 2, 3. Then the last guy I generate, it could be bigger than the measurement time. You fall after the measurement time. But the process stops at time t. So at the yeah. So this is called backward recurrence time. Claude investigated this in the context of renewal theory. And this last time is actually important for rare events. It can be very big. It can be bigger than the other guys, and it contributes. You cannot neglect it. It's important. Okay, so you see with your eye, at least with the correlation plot, okay, this principle works, even though we have this constraint, which means we are not dealing now with IID random variables. But let us try and go forward and prove it. So first thing to do is let us do some argument from extreme value statistics. And the argument is the following. We have n, and I know it's random, but let's say t is large, so roughly speaking, because the average time between turning is finite, then n is roughly t over tau. Let's neglect fluctuations. Then let's neglect the last interval, tau 1 up till tau n, and then we are going back, and then we need to look at the maximum of these guys, which is the biggest guy. So this is simply usual Fréchet territory. So then you look at the probability that t max is smaller than some t tilde. This is the probability that each individual one is to the power n, and then you expand this because I'm taking t tilde to be large. I use the waiting time PDF, and then it's a very simple thing to find this guy. And this was actually proven by Godrej, Majumdar, and Scherer a few years ago. Exactly, I mean, they looked at the exact expression in Laplace domain, and then they could prove this, but this simple argument gives this. So this is certainly correct. There is a but, however. When you think about this, this Fréchet law has a power law tail, which stretches till infinity. This cannot be because the maximum of T max, the biggest jump, cannot be bigger than the measurement time, for sure. So what we did is use these gentlemen's result. We are riding on their tail here, and we refined a little bit the structure of the theory. And we said that because this is true, we looked for a second scaling solution where essentially t is going like, these are the typical fluctuations. We're going to look at the rare events of this Fréchet law, and then we could show the following, that the PDF of tau max, when tau max is of order t, here it's not t, it's t to the power 1 over alpha, behaves like this function. And this function is given by these two, there are two terms. This guy is actually matching the Fréchet law if you work it out. This is simply the tail. And then you have a second term. And the important thing here that this scaling variable y is given by, is between 0 and 1. Beyond that, you are 0. This is obvious because you cannot have a bigger one. And this is, I would say, a second scaling law. It's a simple scaling law when you take tau max to t, and it's a limit theorem. It's independent what is the PDF. So it's as general as Fréchet for this class of problems. It matches Fréchet, and it just has this dual scaling that also Vulpiani was talking about. Because you see here I scaled tau max with t, while here tau max is scaled with t to the 1 over alpha. So you can look at two limit theorems. And this is this duality. You always have two. Like by scaling, there are two scales, and there are two limit theorems, and this will be general. Now, this guy I'm not going to prove because I don't have time, but I'm going to prove more the total displacement, and just remember this factor, alpha minus 1 over alpha. Soon it will come back. So how do you look at the total displacement? So again, let us do the same simple arguments. N is t over tau. Problems deals with summation of IID. We neglect correlations. We neglect everything because this will work for typical fluctuations. This is kind of, all this is kind of well known. So x is sum over chi I till n. Alpha is between 1 and 2, so we should apply the Levy central limit theorem because each individual jump has a fat tail. And then you get, for the typical fluctuations, you get the Levy distribution describing the common, like in usual central limit theorem. This is the typical fluctuations. However, we immediately realize that Levy's central limit theorem here implies that, for example, the second moment is infinity because it would predict naively that power laws continue forever. This is unphysical. So we need to do something slightly better to calculate the rare events. And this is what we do now. Let us calculate the rare events. So what is the idea? We calculate exactly the moments of this Levy walk process. This is done by Montrol-Weiss equation, some machinery. Then we will define a generating function. So you have p, k, and t. And this is given by the moments that we obtained by hard work times k to the power n, and we sum this guy. We will sum this infinite series, and then we'll take the inverse Fourier transform. Now, the only trick they're going to use here, we're going to plug in here the long time limit. Now, you expect if you have pk of t, this is the Fourier transform, you inverse it, then you'll get the density. And then you expect it to be even normalized because when k is equal 0, you get 1. But I will show you the fact that I put here the long time limit here, we will not get a normalized density outside. We will get something that describes only the rare events. This is what happens. And it's a limit distribution of the packet, which is not giving you the typical Levy thing, but it's giving you something complementary to the Levy. So the typical fluctuations will be Levy. The rare events will be given by this scheme. So if we do this, we calculate these moments in the long time limit. We sum up the series. You get in Fourier space, you get this function. Well, there's something horrible here, but only important thing is you have here k times t, which means that x scales with t. This is ballistic scaling. That's already some clue. Okay, then you are even luckier that you are able to transform it back. And then you get the inverse Fourier transform, and I write here a for some asymptotic limit that soon we will explain its meaning. And then you will see here you have this distribution. Well, it's a special distribution because it's not normalized. You have this pole on the origin, so it's not normalized. It's called in mathematics infinite density. We call it infinite covariant density. We can discuss later what the whole background of this. I don't want to go into detail. It has ballistic scaling, x over t, unlike the Levy scaling. And the big jump is dominating. You see this alpha minus 1 over alpha? That's exactly like what I found from the generalization of the extreme value statistics. So this proves by simple transformation that the biggest jump exactly gives the same thing. But here we are using this thing to describe the biggest jump. So of course, this guy gives you all the moments. So the Levy distribution describing the typical fluctuation is wrong, predicting the moments, second moment, fourth moment. This, in contrast, gives you all the moments correctly, but it's not normalized. What happens if I multiply here by x to the power 2 and integrate, it will give you a finite value. The high order moments calculates, repairs the non-normalizability here, and you can calculate moments even though this is not a normalized function. So what does this mean? What does this function mean? If I take t to the alpha and take the normalized density, px of t, and plot it as x over t, so this is meaning I'm looking at the rare events because I'm looking at x plus t, and this is one model. Then this black line is this infinite covariant density for one model, and as time goes by, it approaches more and more to this limit. Now, why is this function giving you something not normalized? Is now trivial. I multiplied by t to the alpha. This guy is normalized, but so when I integrate over position, this guy will give you 1 times t to the alpha. T to the alpha goes to infinity. This area underneath here has to be infinite. Still, it's not normalizable, but it gives you all the moments because I got it from all the moments. So the infinite covariant density means that there is a limit for the PDF that I take multiplied by t to the alpha, and in the long time limit it goes to some function which is x with the scaling x over t. So this is the mathematical limit, and it's complementary to the central limit theorem. So there's another limit. You can scale things differently and get the Levy distribution. So this is describing the rare events with the non-normalized functions. And the idea is that you have two types of observable. For example, the second moment. The second moment is integrable with respect to this and not with respect to the typical fluctuations of the Levy. And the normalization is integrable with respect to the typical fluctuation, but not with respect to this. So that means that there is a critical moment where you have a transition exactly like in the picture given by Vulpiani. And again, this is in perfect agreement with the big jump principle. So again, the center part you can describe by Levy distribution, by a fractional diffusion equation. We can match the two solutions. And then if you look at the moments, so you see this moments, the low order moments are described by what I called before some diffusive. Now we can calculate these amplitudes. How do you calculate these amplitudes? This comes from the typical fluctuation, from the Levy distribution. This guy comes from the big jump principle. Only one jump. From the extreme value statistics, you know the biggest jump, and then you can in principle calculate this. So if you plot these amplitudes, m of q, so, and this is again, this is Vulpiani saying that you have this critical exponent here is alpha equal to. So these moments for low q, they are described by the central limit theorem. These moments here are described by this principle of big jump. And you can calculate them with a little bit of work. There is, of course, a critical moment where Q is equal alpha, and you see here some simulations. In the infinite long time limit, this will actually blow up. There will be some logarithmic correction here. But the most important one point to notice is that if this alpha is closer than 2, then the second moment is the worst moment you can measure. And for example, for the Lorentz gas, the critical moment is the second moment. It will never converge. It will be horrible. So everyone loves the second moment, but in these things, sometimes this is really a bad moment. So we have a general formula. When you have a general distribution of velocities, we have this non-normalized distribution. If you want, you can look in my papers. So just to summarize this, we have the following thing. We have this infinite covariant density with this x over t scaling, and then we can use many models. I just showed you up to now one model, but there is a jump model where we throw away the last tau star. We have a velocity with two states, with a Gaussian, with the exponential. Up here, you have this power law, which is non-integrable, which is the tail of the Levy or the tail of the Frechet law. Here, all this is described by this big jump principle. The tail is not universal because different models give you different things, but all of them are controlled by one big jump, the maximum of these times. If you know that distribution, which I gave you before, you can calculate this distribution. And so there is a rule here. The rule here is one jump is controlling everything up here because you are in the far tail. So now when we realize this, we want to go to more, I would say, more advanced models where you have quench disorder, when you have non-renewal events. We want to elevate the theory and see if it can work for other cases. So when you pay attention to what I was saying and you want to get some physical intuition, what is this telling us? What is this big jump idea saying? Well, the idea is we divide it into, in the schematics, into two types of paths. This is going to be super important. So, for example, you can have a path that you have a lot of scattering, and then you have one big jump, and this big jump is ending at the measurement time. Or you can have a lot of scattering, and then you have this one big jump, and then again, you have a lot of scattering. And these two paths are important for us. They will be different. They will give different contributions in the calculations that I'll present. I'll present the results more correctly. But when you think about this, what is happening here? The typical fluctuations, you have a typical scale. For example, for the Levy walk, you have a scale t to the 1 over alpha. While these big jumps are ballistic, so they scale linearly in t. And then in the long time limit, these are going to dominate if we are looking at the very far rare events. We only care now about the rare events. So what we can say is that along the many collisions, let's throw away if you want to calculate the rare events, let's forget about them because you have many collisions. You just care about one big jump. It can be either here or it can be in the middle of the process, and then we're only going to calculate, in some sense, contributions from one big jump to approximate things. And now, these big jumps happens at sometimes tw. And we can, for the Levy walk, we can estimate this from a rate. The idea is that the number of renewals here is t over tau, average tau. And that means that you have a rate, 1 over tau in this example, that you produce. These are the number of attempts to produce this big jump. And the beauty is that you can generalize this, vaguely speaking. I'm not going here in the details. For example, here we have one straight line, but you can add here the big jump could be some other path, as I'll soon show. So the idea is, let us look at the biggest jump. If we can define it, then we can calculate things and obtain interesting results. So for the Levy walk, just going to the example that I already found it in two different ways, but the idea here is that for large x, the position of the particle is either L. L is the size of the jump here. That's the big jump here. Or if you are landing here, that is, you generated a big jump which actually should have reached here, then it will be simply the t minus tw. So you have either this or this, and then you say we have some rate of producing these attempts, and then you have two delta functions, based on these two guys, and I integrate them, and I'm telling you that if you take x to be large and this lambda L, you take only the power law tail, you get exactly this event. So you can now hope that you can generalize this to more complicated processes. And the reason is very simple. You have only one big jump. Let's forget about all the rest. And let's try and calculate with this all kinds of things. So what we did, especially Alessandro and Raffaella, I have to be honest, they came up with a really beautiful, non-trivial calculation. And this is so-called what we call Levy-Lawrence gas. I would not, there are some experiments on this, similar systems. It's called the Levy glass, but in 3 dimensions. But actually what we care about here is just to have something very correlated to see how this principle works. So the idea here is the following. We have set of scatterers on a line in 1 dimension, and the distance between scatterers is taken by a power law distribution. And then you have a particle with velocity v, and it can be either transmitted or reflected with probability half. This is quench disorder, so you have memories. The particle can come back. It remembers where the gaps are. This power law distribution means that you have kind of a fractal set of scattering centers. And what we are looking at is the PDF of the position of the particles. Here you can have zigzagging between 2 scatterers like that, and you have some memory. You do not have renewal. It's much more complicated models. If you think, what is the n here? What is the number of attempts to make the big jump? This, we can argue, is scaling now. Here I'm using the case alpha bigger than 1. I can, unlike the Levy walk where n was t over tau because it was simple renewal, here n is going like t to the half. T to the half is, what is n here is the number of distinct new sites that you visit along your path. So along your path, because you come back many times, it's like diffusive, the center part is like diffusive, then the number of new gaps that you encounter scales only like t to the half, not like t. This is one out of many differences between the 2 models that I'm going to take into account. Now let us have a very simple argument. It's not exact, but we prove this. But why do we expect the big jump principle here? So let us again go back to the IID case. So here we have a distribution that follows like a power law distribution. And then what did we say? This is the usual stuff. The probability of the maximum of these LIs, these are the gaps now, bigger than R tilde, is 1 minus 1 over this. Then we approximate this for large R tilde. We get n, and this is the power law. This is this PDF of n times x to the minus 1 minus alpha. Now I'm going to argue, I don't have a better way to do this. In the Levy glass, when you have this quench disorder, this n is the number of the renewals of the new scatterers that you meet. Then it has to scale like t to the half, not like t as before. So the PDF, this argument says, okay, here is n, this is t to the half, this is x to the minus 1 minus alpha, because these are these power laws. Then I anticipate the ballistic scaling. So I have here, I just write it as x over t. Why ballistic? Because you move ballistically between collisions. Then I expect, and we can prove that in the limit, when you take this PDF, when you multiply it by 1 plus alpha, a half plus alpha, before it was just alpha, then you'll get some infinite covariant density that will scale like x over t. So this will describe again the large x behavior of this model. And we know from these arguments that this function will have a pole at 0, which is a power law based on these arguments. But anything else to calculate this function is totally not trivial. Because we have this zigzagging motion in this quench disorder system. And for that, we need a real calculation. We have to sum over all the zigzagging paths. Why is it at all possible? Because what we should care about is only one gap. And in this gap, we will have zigzags, and we will calculate. So we should look for the biggest gap, roughly speaking. And then in this gap, you can have collisions that you go backward and forward in the final position. So here you go forward, then you go backward, and then you go like this. So of course, this motion and this motion will cancel each other, and then the final position will be here. So roughly speaking, we will take only the biggest gap. So if you do this, I didn't go into the details, I would say we are in Italy, it's more art than a method, but this is what we have. We get this very non-trivial behavior of the rare events. You see, this is the absolute value of the final position of the particle over t based on this single big gap. Only one single big jump is contributing. So this is the usual scaling. Here I multiply the PDF exactly as I told you before. And in the long time, we increase here in simulations, we increase the measurement time. And as time goes by, it approaches this highly non-trivial purple line. And this purple line, A, has this divergence, which is non-integrable at this small limit, which will correspond to the power law coming from the typical fluctuations. So this is like the Levy walk in some sense. You have this power law. But what is not trivial is, first of all, you have here, you go up here, and if you look here carefully, you see non-analytical behaviors. This is for alpha equal 1.5. I'm not going into details. Just to show you the non-analytical behaviors, they are found for all alphas, and for all alphas they are found at the same positions. And the theory gives you these non-analytics. Of course, when you increase alpha, it's more and more difficult to see them, but that's why I go down in alpha here. I'm not explaining why for this alpha you also see this, but you can see this, and you see the theory, and you see that also the simulations have these non-analytics, and this is found on 1/3, 1/5, 1/7. And these are, roughly speaking, because you have this big jump, you can understand the following. When you are out here, maybe you collided in this big jump only one time. You had one collision, or maybe none. When you are here, you collided many times because your motion is small. What happens here, let's say 1/3, is you have these paths that you collide exactly. So you go back and forward, and then one time back. These two guys will cancel each other, and you'll be in the 1/3, and then 1/5, and 1/7, etc. So these are only on the odd numbers. And the theory, based on the single big jump, gives you these non-analytical behaviors. It's really very nice, in my opinion. I would say not useful at all, only for the brain, but this is what it is. So I don't know how much time I have, not so much. 5 minutes? Okay. For talk or for?
Well, I mean, if you exclude this question, then it's over.
I don't know what to answer. I guess there's no question, so I'll continue. So just some motivation. We also look at the level on the Lorentz gas. So this scattering on the fractal set was a disordered Lorentz gas with a special arrangement of the lattices on a fractal. But now we also looked at the Lorentz gas with infinite horizon. And I said, we show also in the simulation, you have these power laws, which are exactly like, you have a Gaussian and then a power law, which is exactly what you kind of expect. But this is special because what I showed you is when alpha is between 1 and 2, you have a Levy distribution, and then you have something matching it. But here in the center, you have a Gaussian. That is, you are not in the Levy regime. So this story turned out to be much more difficult because you are exactly on the borderline between Levy and Gauss, and there are totally different issues there. This was done by a student called Lior Tsofati. So again, we have this psi of t, but now it's a very special tau to the -3, and this was actually shown a long time ago by many people, that you have this waiting time PDF due to these long travel times in the infinite corridors. And then mathematicians worked on this. Usually if mathematicians work on something, you should either explain what they did and you not try to correct them. Of course, all they did was correct, but what they do is they take the limit t to infinity. And actually, this is, in this particular example, is not so good, in my opinion, because these theorems that tell you that the center part is Gaussian with a logarithmic correction, beautiful mathematical works, they describe the center part of the spreading particles, the typical fluctuations, but they are valid when log of n over log of n is much less than 1. This means N here is the number of collisions of the particle with the scattering centers. But if you take n, this small number, yesterday we had that 16 is a big number, but if you take this number 10 to the 285, if you want this epsilon to be 0, then this is really a big number. It's more bigger than the number of particles in the universe. So because you're working here between Levy and Gauss, you do not converge at all, or very, very slowly towards the limit theorem. And then actually our problem was not to describe the tails, that was also difficult, but actually in the center, if you want a finite time simulation, you have a huge convergence problem. And this we did with some trick called the Lambert scaling that Leo Tsofati, I think, brought from Baruch, but I took it. But I'm not going into the details because I think I'm out of time. But this, if someone wants to talk about this Lorentz gas, this is the theory based on a rescaling finite time that gives you both the center part. This is the theory. These are simulations, and these power laws, and these cutoffs. And out here, we believe there is an infinite density describing the rare events. These big jumps will be describing here these rare events down here. Of course, this is for a particular choice of scatterers. You can make the scatterers smaller, and then you'll see also channels opening here and here. You can get all kinds of geometries, but I'll leave it here because I think my time is done.
Okay, so we have time for a couple of questions.
What will happen if you have some distribution of the velocities? Of course, this is the singularities will be smeared, but
Right.
at some point you will switch to the tail of the distribution of the velocities.
Right, so it depends which model you're talking about, the quenched model or the annealed model. For the annealed model, for the Levy-Walk model, we actually, we have here, sorry, I'm going the wrong way. We have a general behavior for the, you see this equation has in it the velocity distribution, but this model, which is this annealed Levy simple renewal model, doesn't have these non-analytical behaviors at all. So I guess more interesting part of your question is related to the quench disorder. So of course, when you will have velocity distribution, these non-analytical behaviors will go away. We did not investigate this in detail. We were just happy to see these non-analytical behaviors. But of course, yeah, you are right. I mean, with a distribution like a Gaussian distribution, this will be wiped away, and I don't think you will see it.
Yes, so if I understand, in all these models, basically your distribution has somehow two parts. I mean, one which is the typical one, and the other one which is a kind of large deviation, sort of.
Sort of, yes.
And then
Sort of is important.
Then you are saying that somehow you want to argue that this large deviation is due to this big jump scenario.
Right.
But somehow, if I look at the tail of the typical distribution in the Levy case, this is already due to single jump. I mean, it's algebraic.
Right, but
So what's
the new thing is down here. The Levy thing would say, okay, you have a power law, it will continue forever, and that would be Frechet. So already here you have you can say that here Levy and Frechet walk, the usual Levy and Frechet walk. But the single big jump walks where it matters, where you are really at the tail, where you have some differences between the models. So in this figure, we add here a rescaling with the Levy tail. All of them have the same Levy tail. But then they go into some different models give you different things, and then you need the big jump to differentiate them. But of course, you have matching. So the matching in this scale, x over t. So when x over t is small, you get the usual Levy thing. But
I think all these things comes from the cutoff that you have a fixed t essentially. So the cutoff region which gives you different scale. So I have another question for you. I mean, this did you compute the the picture that you showed? For example, if I ask what is the probability that the big jump occurs as the last interval, basically.
you mean
Yeah,
for which model? For
Levy-Walk model. You should have a slide if you go back a little bit of this. Yeah, this is for example. I mean, if I ask what is the probability that the big jump, I mean this first picture, what's the sort of probability of that happening as opposed to this one?
What is the probability? We didn't calculate that explicitly, but we know that these two are contributing. It will depend what is alpha, which is more. When alpha approaches 2, becomes bigger, then this gum becomes smaller. The distribution of this time interval, this is called the backward recurrence time, is all known. For example,
No, I know, but in fact we computed with Claude and Gregory the probability for certain classes of processes basically. But I was wondering if for the Levy walk, I don't know what is the, because for many processes
we didn't
actually most
quantify
of the
this, but they are obviously both important. In principle, you have an equation here, and you can you have two. You just integrate over x, and then you'll get from this guy and from this guy. But I didn't do this calculation. I was preparing my talk.
So I'm just trying to understand this non-normalized density. So
Yeah.
is a divergence occurs from the small x behavior, right? Because we're trying to take the power
Yes.
without a cutoff and without a smoothing, and that's why you get this divergence.
Well, the divergence comes from the fact that you're actually matching here to the Levy distribution. So you are going here to the bulk. So you can say this is a leftover of the Levy density that when you plot it like this, if I would plot everything here instead of x over t, I'll plot this x over t to the 1 over alpha. Then I would see the Levy. And you increase the measurement time, it will, in the long time limit, approach the Levy. This is how many people have plotted these type of things. They assume the Levy scaling, and then they plot it this way. But I choose to plot it differently. To blow up the large fluctuations, I plot it to x over t, and then multiply by t to the alpha. And then you see a different limit. But the point is, you can choose how to scale your data, and it will either approach this non-normalized state or the Levy state. So there are two scalings. Again, this is the general agenda of Vulpiani, that you have dual. It's not like bisexual, but by both diffusive and ballistic together. So you have two limit theorems.
Difficult to get a crossover function.
No, you match them. This is the matching is not difficult. In the Levy walk case, it's not difficult. But actually, I would say for the quench disorder, it is difficult. In fact, no one knows what is the distribution of the quench disorder Levy glass in the center part. So we are in a very strange case where we know the rare events, but we don't know the typical events. Because in these models with these correlations, the typical, when alpha is less than 1 actually, there's no theory about how exactly the typical behave, because it's not Levy and it's something else, and no one knows what it is. Mathematicians tried to find it, but they couldn't. So it's really bizarre that we can calculate the rare events without the typical events. We know some things from simulations, but that's it.
Okay, so if there is no other question, let's thank Ali again.
So hello everyone. I'm Tal Agranov, a PhD student of Baruch Merson here in the audience. I would like to thank the organizer, David Holtzman and Gregory Sher, and also Baruch Merson, for giving me this exceptional opportunity to speak here. I'm going to be telling you about a work which was done together with Baruch about a narrow escape of interacting particles. So I'm going to start by briefly presenting the narrow escape of a single particle, and then I'm going to talk about how one can use the results of the single particle theory to address a narrow escape of many non-interacting particles. But our goal in this work was to address narrow escape of interacting particles, where not much is known. And we were able to do that by employing the macroscopic fluctuation theory. So we employed it here for the first time to the narrow escape of interacting particles. And it enabled us to obtain the new results, which I'm going to be telling you about. And I'm going to finish by briefly discussing future possible applications. The narrow escape problem, which is a term, if I understand correctly, first coined by David Holtzman and Zev Shus. Okay. So I'm sure many of you here are well familiar with this problem. In fact, leading experts are sitting here with us. So in the basic setting, one considers a Brownian particle which freely diffuses inside the bounded domain, except for a very narrow escape window on its boundary. And the basic question is, how long will it take that particle to escape from the narrow escape window here? This problem has many applications in different fields, like chemistry and cellular biology, and also other fields. You might imagine that this molecule is this Brownian particle is a specific molecule that diffuses inside the cell, and it needs to reach a certain reaction site on its boundary. And the time it will take it to do that will set the rate of an associated biological process. So this problem drew much attention in the past 20 to 30 years, and actually a lot is already known about this problem. It is already a mature theory, and I'm only going to present the most basic concepts and results that will serve us in what's to follow. So the basic quantity that characterizes this process is the non-escape probability, the probability that the particle did not escape the domain up to a certain time t. As the decay rate of this non-escape probability gives us the distribution of the escape times out of the domain, and it also gives, in a simple way, the mean escape time by the time integral over the non-escape probability. So, however, as was shown by a series of works, the mean escape time can be sometimes misleading in the sense that it can be orders of magnitude away from the most expected, most probable escape time. So the bottom line message here is that the knowledge of the non-escape probability is important to this problem. So how do you find it? Well, it is just a volume integral over the position density distribution of the particle inside the domain, which obeys a diffusion equation inside the domain with these mixed boundary conditions, the zero probability flux boundary conditions on the reflecting boundary, and the vanishing of the probability on the escape window, as we assume that particles that get out do not come back. And the solution is given by eigenfunction expansion over the eigenfunctions of the Laplacian inside the domain with these mixed Neumann-Dirichlet boundary conditions. And the resulting non-escape probability is given by a series of decaying exponents whose decay rate are the principal eigenvalues of the Laplacian. So this seemingly simple formal result is actually hard to compute explicitly for a general geometry, mainly due to the complicated mixed boundary conditions. However, major progress was made in finding it explicitly for some special symmetric geometries, and also deriving approximation schemes to have it evaluated. However, in two important limits of short and long times, one can obtain some general expressions for this non-escape probability, which are quite universal and are given by the basic quantities that characterize the process. So the simpler limit is the one of the long times, where it is evident that the series is dominated by the leading term, as all other terms are exponentially small at these long times. And this also describes the fact that the process becomes memoryless at these long times. The mechanism behind it is that given that the particle hasn't escaped the domain up to these long times, it already explored all parts of the domain. So the probability of it to escape at each instance, given that it hasn't escaped up to that time, becomes independent of time. And the principal eigenvalue, which gives us the decay of this exponential distribution, is very small in this limit of the narrow escape limit. And this makes the mean of the exponential distribution well within the long times we consider here, and it gives us the leading order approximation for the mean escape time. So before we proceed to find this principal eigenvalue, let's ask whether one can relax the requirement of long times. So what happens at shorter times, of course, depends on the initial condition. And it turns out that for a certain initial condition, indeed, we can relax this requirement. If we assume a uniform initial condition, which I'm soon going to elaborate more about this initial condition and its importance, then if we assume that, then the exponential decay starts much earlier. And this is also reasonable, as this initial condition states that the particle already explored all of the domain from the beginning of the process. So how do we find the principal eigenvalue here that gives us the decay rate? Well, one method of doing so is by matched asymptotic expansion. As the principal eigenfunction is varying over very short scales in the vicinity of the escape window, the scales of the escape window itself, while approaching at constant value away from the escape window. And this means that at the vicinity of the escape window, the eigenvalue equation can be approximated to be just Laplace's equation, as the leading term here dominates due to strong special derivatives. And the solution is given by an electrostatic analog of via the electrostatic potential around this conductor shaped as the escape window. And this is why the resulting leading term approximation for the principal eigenvalue is given by the capacitance of such escape window, which indeed scales as the length of the escape window. This gives us also the famous result for the mean escape time in the narrow escape problem. So this was the long times behavior. What about the short times? At short times, the series representation is, of course, ineffective, as all terms in the series are important. And also, the behavior at these short times is, of course, strongly dependent on the initial condition. So two major initial conditions that were extensively studied in the past are deterministic, which David talked about yesterday, where at t equals 0, the particle is initially positioned at the specified location inside the domain. The other is equilibrium, or a annealed initial condition, where one assumes the particle had a long time to explore the domain without getting absorbed, so its position is uniformly distributed inside the domain. When at a certain instance the escape window becomes available, and one asks how long will it take the particle to escape from that moment on. One can also look at that initial condition as the average overall deterministic initial conditions. So this is also meaningful, as the initial position of the particle can fluctuate over different realizations of this process, and meaningful question will be how will the average overall these initial conditions behave. So for that uniform initial conditions at short times, only the very close vicinity of the escape window is affected, where the position distribution is varying over very short scales, the diffusive length scales, that grows like the square root of time. And at these short times, it is much shorter than the size of the escape window. So one can approximate the escape window to be just an infinite plate, and the problem is reduced to one-dimensional into with respect to the normal direction to the escape window. So here one needs to solve a one-dimensional problem of non-escape against absorption at the origin. So this one-dimensional problem is exactly solvable. And to obtain the result for a three-dimensional case, one just needs to plug here an effective one-dimensional density in the normal direction to the escape window. So these were the two short and long times asymptotics for the non-escape probability of a single particle. However, as David pointed out yesterday, in many situations you have many escapers who are trying to escape this domain, and an important question will be how long will it take the first of them to escape. So these are all equal players in this game, they're all trying to escape, and you're interested in the time at which the first of them escapes. So if we assume they are all non-interacting particles, then their non-escape probability of the ensemble is obtained from the single particle non-escape just by raising to the power of n the single particle non-escape probability. And importantly, this non-escape of the ensemble gives the distribution of escape times of the first of these escapers. So if we plug in here just the long times asymptotics of the single particle result, we retain an exponential decay of the ensemble non-escape probability at long times, where the decay rate is just n times faster. We denote it by the density, just their number over the volume. So this means also shorter escape times of the first of them. And importantly, if there are not too many of them inside the domain, then the mean escape time is still much longer than the long times we consider here, and it is given by this exponential exponential decay, and it is n times faster than the single particle's mean escape time. When I'm saying not too many of them, there could be still many particles inside the domain, just not too many of them on the small scale of the escape window. However, if there are much more particles than that on the domain, many of them on the scale of the escape window, we have a different behavior, which is dictated by the short times asymptotics of the single particle non-escape. So if we plug the single particles non-escape, raise it to the power of n, and use the representation of the exponential function, we have a stretched exponential decay over time of the non-escape probability. So it is different than the other initial condition David talked about yesterday. So here we have a stretched exponential decay over time at short times. And for large number of particles, this gives us the mean escape time, which is decreased by 1 over their number squared. So what we see here in the graph is a crossover between the 1 over n to the 1 over n squared decrease in the mean escape time. And it agrees very well with the extensive Monte Carlo simulations which were performed here. So what about real experiments? So indeed, advances in the tracking of single colloidal particles makes it actually possible to measure the escape times in this system. And in this work here, they built a micrometer device with a nanometer escape window on it, and they could trap inside a desired amount of particles and could actually measure the times at which the first of them escapes. And they report deviation compared to the single particle-based non-interacting picture. So they assume there are interactions between the particles, and this could actually describe real biological systems. So this was our goal here in this work, to address the effects of interactions on this problem, where the single particle theory is ineffective here. And if you try to treat this problem from an individual particle microscopic picture, the problem is very hard, because there are correlations between the particles due to interactions. So what can be done in this case? Well, in this case, where the microscopic picture is hard to address, a macroscopic coarse-grained description has a clear advantage, and this is the approach we took here in this work. But before I describe the coarse-grained description we used, one needs to first declare what is the underlying interacting, the model for interactions between the particles. A model for interactions is given by diffusive lattice gases. These are a family of models which are defined microscopically by particles which are placed on a lattice and hop between lattice sites with the prescribed fluctuating probability rates, which may depend on the local site's occupation. So the simplest example will be that of non-interacting random walkers that can hop to each adjacent site with equal probability independent on the site's occupation. So importantly, this model, when coarse-grained on macroscopic scales, coincides with that of non-interacting Brownian particles I just talked about before. A simple model for interactions could be the simple symmetric exclusion process, the SEP, which accounts for excluded volume interactions between particles. So here particles can only hop to vacant sites. So these are only two examples. There are many more of them which take into account different types of interactions. And if we coarse-grain the dynamics over the microscopic scales of lattice constant and hopping rate, we arrive at a coarse-grained description of the dynamics, assuming there are many particles on the macroscopic scales, which is given by fluctuating hydrodynamics. So basically, it is a Langevin equation for the particles number density and flux. Okay, so what it states here, it is a conservative equation for the particles density inside the domain, which on average obeys some sort of a diffusive behavior where the diffusion coefficient might depend on the local density. But this diffusive flux is also fluctuating as the process is stochastic. And the noise term here it takes it into account. It is delta correlated over the macroscopic scales we consider here. And the amplitude of this noise can also depend on the local density. Okay, so these two functions, the diffusivity and the mobility, are the only ones needed to characterize the process on the macroscopic scales we consider. And they can be derived, and it was actually done, from the microscopic underlying dynamics. Okay, so it was done rigorously, and it was proven that for the random walkers and for the SEP, the diffusion coefficient apparent here is constant. For the random walkers, the mobility grows linearly with the density, and for the SEP, it is a nonlinear function. So importantly also, I want to note that this Langevin equation is also a good description of many real physical systems whose underlying dynamics is not discrete. So examples could be the transport of electrons at low temperature or wave propagation in disordered media. So now that we have a coarse-grained description for the dynamics, we need a formalism that will enable us to extract probabilities of macroscopic observables, such as the non-escape probability we're interested in here. And that is given by the macroscopic fluctuation theory, the MFT. So I'm sure many of you here are familiar with it, or at least heard about it. It was developed, and it's still being developed in the past 30 years, and it had several contributors. And it was originally formulated in other contexts, mainly in the context of current fluctuations in open systems. These are a system of a gas, which is brought in contact with two unequal density reservoirs, and one is interested in the fluctuations of the number of particles flowing through the system. But later on, it was employed to other problems, such as void formation or activity fluctuations. And we found this formalism suitable to treat the narrow escape problem of interacting particles. And we employed it here for the first time to this problem. And with it, we obtained some new results. So I'm only going to review the most basic concepts that will serve us. So the starting point for the MFT could be a path integral formulation for noise realizations in the Langevin equation. And if we use the algebraic relation between the noise and the density and flux, we have a path integral formulation for observing joint density and flux histories of the system, which are constrained by the conservation law. When the weight, the probabilistic weight of each history is given by the exponent of this action functional. So this gives us the probability of observing a specific history of the system. So within this path integral picture, the probability of non-escape is given by evaluating the path integral only over the histories that led to particles non-escape. So the MFT, it uses the macroscopic scaling of the system. Yeah. So okay, so here I write the notation here is quite obscure maybe, because I didn't specify what is the domain of integration. Once you specify on which histories you integrate, it gives you the history for the probability for an associated observable. So when I do not specify, this is just normalized to 1. So yeah, we are interested in the survival probability. So we are interested in evaluating this integral only over the non-escape histories.
How do you translate this no-escape history on the history of rho and g?
How do you relate eta to rho and j?
No, you tell I evaluate this probability just at history which don't escape.
Yes.
And I don't see directly how you translate the fact don't escape on the history on the rho and the history of g.
Okay, so you just evaluate the particles flux to the boundary, and for histories where this integral is non-zero, then they do not survive. So you only are interested in histories where the flux integral or the flux, the normal component of the flux towards the escape window is zero, identically zero at all times. So this is a certain. Yes, you can enter it as a delta function constraint, and using exponential representation of the delta function, you can also enter here as an additional term in the action functional, and all of that can be taken into account. I'm not going to go well into the details. As we'll see, there are not. Yeah.
I can have just a basic question that when you use this Martin Cicero's formalism, you go from eta to j rho, so Jacobian is one,
No, so in general, yeah, it's a good remark. Of course, you need to take into account Jacobians, which here they are, of course, not trivial, but they're all hiding inside this path measure, which I'm not specifying. But yes, of course, there are also Jacobian. But within the MFT, the Jacobian is not important because the MFT gives the evaluation of the non-escape probability by just a saddle point evaluation of this path integral. So for macroscopic systems, the non-escape probability is dominated by the minimal action. Okay, so the minimal action meaning the action evaluated over only the most probable histories that led to particles non-escape. So these are called also the optimal fluctuations of the system, and this means that one has to minimize the action functional over the constraint of particles non-escape. So this results in Euler-Lagrange equations, whose Hamiltonian formulation are known as the MFT equations. So these are coupled equations for the optimal density histories and conjugate momentum fields. And these are also furnished with the problem-specific boundary conditions in space and in time. And as you can imagine, these coupled nonlinear PDEs are in general hard to solve analytically. However, in the two important limits of short and long times, which I discussed in the single particle context, major simplification arises, and we were able to solve this problem.
So is small p the same as a capital P, or?
Where? Yes. Okay. So here P.
No,
You.
I think at the bottom of the equation.
Where?
P.
Okay. So sorry. P here and okay. This is a bad notations. P here.
It's small and that one is big.
Yeah. Okay. So.
But it's the same, right?
Yeah, no. So here P here is the conjugate momentum field for the optimal flux, optimal density history. And P here is the actual non-escape probability which we are looking for. Okay, so what happened at long times? Well, at long times the system follows an additivity principle, which means that the optimal histories of the system we're looking for approach stationary profiles. So this additivity principle was first conjectured in an entirely different context of current fluctuations in open systems. But it also holds for our problem of narrow escape. So plugging in zero flux and constant stationary density profiling into the action functional gives us immediately an exponential decay over time of the non-escape probability, where the decay rate is given by a simpler time-independent minimization problem. So for interacting particles as well, we retain an exponential decay over time of the non-escape probability, though the mechanism behind this exponential decay is different than the one behind the single particle case. The reason that for also interacting particles, the non-escape decays exponentially over time is that at long times, the non-escape probability is dominated by noise realizations, which prevent particles from escape by establishing a stationary profiles of the density. Okay, so the cost of maintaining the stationary profile is growing linearly with time, and this gives us the exponential decay over time of the non-escape probability. So the simpler minimization problem for the decay rate here can become even simpler if we use a variable transformation, which is given explicitly in terms of the gas coefficients. And in terms of this auxiliary variable, the action rate functional is reduced to an electrostatic energy functional, which is of course much simpler. So how does the Euler-Lagrange equation of this functional looks like? Well, they take the form of a nonlinear Poisson type of equation, where the nonlinear term here is due to the constraint of particles conservation. So you were worried how to impose the conservation of particles, so you do it by a constraint minimization, and it is preceded by a Lagrange multiplier here. So this, in general, nonlinear equation is more complicated than the eigenvalue equation we encountered in the single particle long time non-escape. But it is much simpler than the coupled nonlinear MFT equations we started with. And moreover, it appeared in many other contexts. For instance, it is the equation for the stream function in the two-dimensional incompressible flow, where much is known about this type of equation. Also about it appears in reaction diffusion equations at steady state, and the equation for the temperature distribution inside reactors at steady state, where the nonlinear term stands for the reactions. So let's first get convinced that this formalism reproduces the exact result we obtained from the microscopic picture at long times for non-interacting particles, where it is obtained from the single particle theory. So indeed, if we plug in the gas coefficients of non-interacting random walkers here, we arrive at a linear Helmholtz equation, or the eigenvalue equation we already encountered in the single particle theory. But here it is for entirely different entities. For the single particle, it was the equation for the the particle distribution inside the domain. Here, this equation stands for the optimal gas profile against absorption. So if we plug in the solution into the action functional, we retain the exact result we obtained from the single particle theory. So this is encouraging. Here, this is the particle's density. This is the n divided by the volume. No, so, okay, so when I'm saying single particle theory, I mean that we considered the case of many non-interacting particles, where the non-escape is obtained from the single particle theory, and you just have a factor of n.
What's this constant C?
Okay, C is the capacitance of the escape window. I mean, the capacitance of the conductor shaped as this escape window, which is the leading order approximation for the principal eigenvalue here. Okay, so this was a good test, but once we consider interactions, interacting models, this Poisson equation is nonlinear. However, the same type of methods that helped us to solve the linear case can also work for the nonlinear case, namely matched asymptotic expansion. So the nonlinear version of this was developed in a different context to find the temperature profile inside an insulated reactor, except for a small cooling patch on its boundary, where similar equation and boundary conditions appear. And in that case, it was shown, just as for the linear case, that the profile we're looking for is varying over very short scales given by that of the escape window in the vicinity of the escape window, and while approaching a constant away from the escape window. So the underlying picture behind this is that optimal noise that prevents particles from escaping is doing that by creating a very small depletion zone around the escape window, where it needs to work and try to prevent particles from escape, while across most of the domain it don't need to work, and the gas is just uniformly takes a uniform value. So because of these strong special derivatives in this vicinity of the escape window, the leading term here dominates over the second one, and we can approximate this equation to be just Laplace's equation, which is surprisingly universal to all the gases. So the solution is given again by the electrostatic potential around the conductor shaped as this escape window. But interactions, of course, do matter, and we see them once we go back to the original variable, which is the optimal density profile, which we look for by acting with a nonlinear in general function over this universal electrostatic potential. So the optimal profile for surviving is, of course, gas specific. And once we plug it back into the action functional, we obtain the decay rate of the non-escape probability, whose geometry dependence is universal and again given by the electrostatic capacitance. But the interactions between the particles is encoded in general nonlinear dependence on the gas density. Okay, so let's see how this result looks like, for instance, for the SEP. If we plug in here the SEP's coefficients, we have the decay rate for non-escape probability goes like the arcsine square of the square root of the density. So importantly, this decay rate is faster than that of non-interacting particles. And this is also reasonable on physical grounds, because particles that has excluded volume interactions are less likely to stay inside the domain. It is harder for excluded volume particles to stay inside the domain compared to particles that can just cross over one another. However, at very low densities where the interactions can be neglected, we again coincides with the linear dependence on the density as we obtain for random walkers. So this is the long time behavior of non-escape of interacting gases. What about short times? Well, here the additivity principle breaks down, and the problem is more complicated. However, the optimal profiles, optimal histories we are looking for are varying over, again, short scales, the diffusive scales, which grows like the square root of time, which is much shorter than the size of the escape window. And this enables us to approximate the escape window to be an infinite plate, and we are reduced to a one-dimensional problem, but this is a different problem than I discussed in the single particle case. Here, we solve a one-dimensional problem of an interacting gas against absorption at the origin. So we need to solve the MFT equation, that time-dependent MFT equations, coupled nonlinear equations, but only in one special dimension. So this is still a hard problem, but it was already addressed in this work I cite here. And it was found that the MFT can yield a low-density expansion for the non-escape probability. And if we use this result to our three-dimensional case, we have that the non-escape probability decays like a stretched exponent. Again, we retain a stretched exponential decay, even though we have interactions. And this is due to the reduction to a one-dimensional problem where the only relevant scale is the diffusive scale, which grows like the square root of time. The geometry dependence is also universal, and it also has to do with the reduction of a three-dimensional to a one-dimensional problem. And the effect of interactions is encoded in this nonlinear in general function acting over the density. So this is a gas-specific quantity. So the two asymptotics of long and short times are summarized here. At long times, we retain an exponential decay of the non-escape probability with the universal geometry dependence. At short times, we have a stretched exponential decay with a different universal geometry dependence. And the effect of interactions is encoded in two different gas-specific density dependencies, which in general are nonlinear. And they are different because they had to do with different quantities, different processes. At long times, this density dependence has to do with the cost of maintaining a stationary gas profile against absorption, while at short times it has to do with the evolution of the optimal time-dependent history of a one-dimensional problem for non-escape. For the random walkers, if we plug in the gas coefficients here and here of the random walkers, we reproduce the exact result we obtain from the microscopic picture for non-interacting particles, where these two functions are linear, they are the same. What about intermediate regime, or in general, whenever the MFT problem is more complicated? It could be from many reasons. Well, in that case, it can still be addressed by a numerical scam, which was developed by Chernych and Stepanov, and it was already implemented to the MFT in several contexts successfully. So whenever the MFT is too complicated, one can still attack it numerically. What about the mean escape time? Well, just as for non-interacting particles, when there are not too many of them, this mean escape time is very long, and it resides in the long times asymptotics, and it's given by these asymptotics. And for very large number of particles, it is in the short time asymptotics given by this expression. For intermediate densities, we expect a crossover between the two results, just as we saw for random walkers. So I would like to finish with a few words about possible future work. The MFT is very versatile, and one can incorporate into the MFT many additional effects which were already considered in the context of a single particle non-escape. So a few of them are, for instance, what is called an energy barrier at the escape window. This is a situation where particles that reach the receptor or the escape window do not escape or bind with probability 1. This can be due to the fact that it has to be with a certain orientation relative to the escape, the receptor, in order to bind to it. So this was proven to have dramatic effects for a single particle. Another will be a finite lifetime of particles, when particles are disintegrating while diffusing into the escape window. So the MFT can incorporate arbitrary reactions between the particles. It was already implemented in different works which employ the MFT, and it could also be implemented here for the narrow escape. And also active transport modeled by an external driving field acting on the particles, such as in chemotaxis, for instance. So this is also a built-in feature of the MFT and could be incorporated here. Of course, numerical simulations are very important to check our results. This will be Monte Carlo microscopic simulations of the underlying dynamics. And these are not trivial, as we have an additional small parameter in the problem, the escape window. So there should be many sites on the scale of the escape window, and much more than that on the scale of the entire domain. And lastly, experiment. It will be very interesting to check whether the diffusive gases can actually model real systems of colloidal particles. The MFT, the diffusive gases, has an additional fitting parameter, which is the size of the lattice constant, which could be fitted to some effective size of a colloidal particle, and it will be interesting if that could work. So as you can see, there is a lot to be done within the MFT. And with that, I would like to finish and thank Baruch Merson, and thank you for listening. Thank you.
Thank you very much.
Very interesting results. I have the two questions. First, is it possible to extend the short time results for fixed point? Because I expect that you consider just average one.
Okay, so you are talking about the deterministic initial condition. Okay, so I think I have maybe a slide on that. Well, if they are not, well, at long enough times, we still expect an exponential decay for the non-escape, but under a different condition. Okay, I'm sorry. So this this exponential decay will still yield the mean escape time for not too many large number of particles inside the domain. For a much higher number of particles than that, the mean escape time is much shorter, but it is still dominated by scenarios where the gas is dilute when single particle reaches the escape window. So it is in some sense reduced to the picture of non-interacting particles. So I expect the same 1/log n dependence as for the deterministic initial condition at very large number of particles. So the interactions at these very large numbers can be neglected, as it is dominated by single trajectories that escape the cloud of particles which is concentrated in some point.
In general, it's possible to apply your approach for all types of interactions, not only volume exclusion, but others.
Well, this approach works for all diffusive gases. So you have long-range interacting models and many other types of models which you can consider.
So just one comment on this. So in a series of papers that has nothing to do with what you mentioned, we looked at the interaction with electrostatic in the context of electrophysiology, where you have to solve not only diffusion but also the Poisson equation, which created forces and create long-range forces. And actually, it's still not clear what are the final results, but we could see that under some regime where you have a lot of particles, a lot of charged particles, actually the motion occurs not through the bulk mostly, but can occur through the surface, and then the escape time is not associated to what you present under C epsilon has to do with this capacity effect, but what happened on the surface.
Yeah, so it's reduced to a two-dimensional problem. Is that what you're saying?
It's in between. It's in between. It diffused in a boundary layer
Mm-hmm.
that you can characterize between the strength of the force and the diffusion coefficient. Basically, define this layer. But in general, I don't know of a good framework to address this question. So maybe if you have time and if you're interested, it would be interesting. I mean, I would be interested in looking at how we can understand escape time in this context where you have this interaction through the electric field, and the electric field is changing because particles are moving all the time, and yet you can have difference of concentration in some places that can induce a difference of voltage, especially when the current is flowing inside the cell. There is a difference of potential that can be transiently generated that can affect ultimately the mean first passage time at the intermediate time scale.
Mm-hmm. So you're
That's a general
okay.
opening, general question that
Mm-hmm.
maybe you have some interesting framework to address something that 10 years we didn't.
Okay.
We made some progress, but not sufficient.
Maybe you mentioned it. Is there some regime where you can just simply change the single particle picture with an effective diffusion constant which is renormalized by the interaction?
You're saying that looking at one particle out of the ensemble, and
I mean, when you have diffusion process, when you have interacting system, you change the diffusivity of the system, obviously. I know. I'm asking him, not asking. So I'm asking, is there a regime, I'm not sure there is, where you just renormalize the diffusion constant and just use the whole theory by the renormalized diffusion?
well, I'm not sure. I'm not sure. I know that for the SEP, for instance, in one-dimensional geometries, people looked at the properties of a tracer particle and take into account the effect of interactions between all the particles by looking just at the position of a single particle, and the behavior there is not diffusive. Yes, this is a property of a one-dimensional. Yeah, exactly. But this is also a different question than we ask here. We ask here about properties of the entire ensemble, not of a single particle. So.
Okay, so let me just ask a question that instead of you are so far looking at just one hole, right, in your listings. If you have more than one hole, let's say two holes, and if you ask,
repeat your question.
okay, if you have a boundary with let's say two holes, through which you can escape, and if you ask, what is the probability, for example, I escape through B, not through A,
from. Okay.
So can you use the MFT, in some way to calculate this hitting probability of one of the targets before the other one?
Well, actually, in the previous work, we exactly discussed the case when there are multiple patches in a different geometrical context, the exterior problem. But yes, we actually probed the joint distribution of absorption into several patches, and this can also be taken into account within the MFT. And we found also interesting results that correlate the absorption currents and the type of interactions between the particles. So this is a new feature for interacting particles.
Okay, if there is no other question, okay, let's thank the speaker again and move to the
So first of all, I would like to thank the organizers for the invitation. The results I would like to present to you today have been obtained in collaboration with several people, with Yossi Klafter for the first part of the talk, Raphaël Voiturier with my main collaborators on these questions, Sylvain Condamin, Nicolas Leverny, and Thomas Guérin, who have been PhD students and postdoc in the group. So the type of questions we've been interested in is very simple to define. How long does it take a random walker to find a target site? As you know, this time is known as the first passage time, and this is a key quantity of random walk theory. Actually, many physical processes are controlled by first encounter properties. At the microscopic scale, this is a case of diffusion-limited reactions, simply because before reacting, particles have first to meet, and this first step of the reaction is typically a first passage event. At the macroscopic scale, such processes in general, for instance, animals looking for food, are efficiently quantified by first passage times.
So finally, this quantity is relevant at different scales. And the first step consists in determining its mean, the so-called MFPT. And in the following, I will restrict myself to the case of a symmetric random walker. When you want to determine this quantity, MFPT of a symmetric random walker, a key parameter of the problem is to know if you have or not a geometrical confinement in the problem. In the absence of any geometrical confinement, if you consider, for instance, a two-dimensional random walker on an infinite plane, you know that you're sure to reach any point of the plane, but the time taken can be very long. So long that, in this case, the MFPT is infinite. If now you put a geometrical confinement that acts as a reflecting confinement for the random walker, the situation is crucially different. This time, the MFPT becomes finite. The question, of course, what is the value of this MFPT, and how does it depend on the confinement? And this is the question I'd like to discuss today. So, of course, this question has a long history, and very schematically, you can classify existing contributions as follows. Most of the work that leads to explicit expressions actually concern one-dimensional or quasi-one-dimensional geometries. If you want to go in higher dimensions, it is much more difficult to obtain explicit expressions. However, a notable exception concerns a specific case where the starting and the target points are actually identical. In this case, you want to determine first return times, and there is an exact formula due to CATS that allows you to express the mean first return time at the inverse of the stationary probability of the target point. In the case where the system is homogeneous, this is simply the number of sides of the lattice. Another class of situation where you can obtain explicit results concerns the case where you average over the starting position of the random walk. In this case, people talk about global mean first passage times. And for example, you can obtain explicit expressions for deterministic fractals. But of course, in this case, because you average over the starting position, you lose the information over this starting position. And this is an information I especially would like to discuss today. Finally, we already heard about these narrow escape time problems where you have a small window in an otherwise reflecting domain, and you can obtain this narrow escape time mainly for regular Brownian diffusion. Determining first passage time in confinement is not only a theoretical problem in its own right, it is actually involved as soon as you consider reactivity in confined media. If, for instance, you consider a biomolecule that has to react at a specific location of a confined volume, what can I do?
You should try to stand on the other side, you know. Everything
this way.
Depends on the capacity and other things. On the
Better?
other side of the screen.
The other
Just
side.
try.
Okay. Sorry? No, I don't have any mobile. Tell me if it's better like this?
It's just some feedback.
Yeah.
Yes,
But I don't know how to remove it. Sorry.
Don't go too far from the center.
Okay. So I stay there. Okay, so in this problem, we have this biomolecule that has to react with another guy in this confined environment, which is typically what happens in the cell. And if you want to understand the global kinetics of the process, the first step required is to know how much time it takes to go from a given point to another one. So more specifically, today we'll be interested in the following questions. First question, how does the MFPT depend on the confining volume n of the system? We say that this quantity diverges with n. The question now, at which speed? Second question, what can be said about the dependency of the MFPT on the distance between the starting point and the target point? Of course, we can guess that if we want to react quickly, we have to start close to the target. An especially important question I'd like to discuss today is the following. Is the initial position of the reactant really an important parameter of the kinetics or not? And finally, are we still able to answer these two questions if we do not consider a regular Brownian motion anymore, but a more complex transport process involving, for instance, the effects of crowding and leading potentially to anomalous diffusion? So what I would like to do is to present a method of calculation that allows you to answer explicitly these three questions. So more precisely, I will present the method first in the case of a Markovian process in confinement, and then I will try to show how you can extend partly these ideas to the case of a non-Markovian process starting with the case of a polymeric Roos chain with a single reactive monomer, then going to the case of a Gaussian process with stationary increments, and finally considering the general case involving potentially aging in the system. And if I have time, I will try to draw very schematic conclusions on reactivity in confined media. So let us start with the first part, first passage time of Markovian processes in confinement. And here I will present only the mean. So the first step actually relies on an exact expression of the MFPT, true for Markovian processes, which relies itself on the so-called renewal equation, which relates two key quantities of random walk theory, the propagator and the first passage time density. We already heard about this equality. I just would like to remind you what it is. You can actually classify all trajectories that go from point Rs to point Rt at time t as a function of the first passage time t prime at which this point Rt is visited. So in red, you have this first contribution of the point t, this is the first visit of t, and then you demand that the random walker comes back to the same point in the remaining time t minus t prime. And because the process is Markovian, you can forget everything about the past at this step. Now you sum up over all possible realizations of the first passage time t prime. This equation is a temporal convolution. It is convenient to study it in Laplace transform. And if you go to the small Laplace variable limit, you finally obtain an exact expression for the MFPT obtained by Noah and Rieger in 2004. It involves n, the volume of the system, the number of sites enclosed in this domain, and h, which is a pseudo-green function of the system, defined as the time integral of the propagator minus 1 divided by n. So this equation is very general, it is very nice, but at this stage it remains formal because it involves W, the propagator, in the presence of the confinement, which is a complicated object in the general case. But
Where are
the boundary conditions, you mean here?
Is it completely general?
No, you have reflecting boundary condition, not completely general, okay? But this propagator is the propagator in the presence of this reflecting boundary condition. So now the question is, how can we go further and obtain explicit results? This equation is formal, but it is actually very well suited to large volume asymptotics of the MFPT. Very simply, if you start from this equation and divide both members by the volume of the system and go to the large volume limit, you're back to determining this difference of g functions, define themselves like the large volume limits of the h function, by definition this object, and finally you're back to determining the time integral of W infinity, which is this time the infinite space propagator. Of course, a much simpler quantity. So at this stage, I would like to do two remarks. First, I would like to stress that what we are doing here is not a severe infinite space approximation of the MFPT. The MFPT itself, we already said it, diverges with n. What we are claiming here is that provided that this difference of g function is well defined, we have extracted the main contribution of the confining volume. And second point, as I will show you in a few slides, even if it's true for large volumes, strictly speaking, this asymptotics provides actually useful approximates even for finite systems. We can show that by comparing with numerical simulations, even if the notion of smallness is not easy to precise a priori. So if we are dealing with regular Brownian motion, W infinity is perfectly well known, and we are done. If now we want to cover more general cases, we have to make an extra assumption on W infinity. And the extra assumption we made is a scale invariance hypothesis for the infinite space problem. It relies on the introduction of two dimensions, the fractal dimension and the dimension of the walk. I just would like to remind you the definition of these two quantities. So we consider a general infinite system. We draw a circle of radius r in it, and we ask two questions. So first question, what is the number of sites of the structure enclosed in the circle? If this quantity behaves like a power law, this defines the fractal dimension of the medium. This is purely static quantity. Now we are interested in a dynamic quantity. We put a random walker at the origin of the circle and ask another question. What is the time taken to this random walker to exit the circle by any point of the circle? If this quantity also behaves like a power law, this defines this time the dimension of the walk. For instance, for regular Brownian motion, dW is equal to 2. Now, with the help of these two dimensions, a very standard scaling assumption for the infinite space propagator is the following. It involves pi, a scaling function, whose argument is a combination of space and time, whose definition can be directly inferred from the very definition of the dimension of the walk. And there is a prefactor, which is here only to ensure a proper normalization of W on the structure. If now you put these two things together, large volume asymptotics and scaling assumption for the infinite space propagator, you can obtain a general result that allows you to answer explicitly to the questions raised in the introduction. So first question, what is the dependency of the MFPT on the volume of the system? What we find is that for Markovian process under the scale invariant hypothesis, we always obtain a linear dependence of the MFPT. And this is not a result that you can infer directly, because you have at least two length scales in the problem, the one associated to the confinement of the system and the one associated to the starting position of the random walker. Second question, what can be said about the dependency on the starting position? This time we have to consider several cases. In the case of what is called non-compact exploration, transient random walks defined by dW less than dF, in this case, this parameter is involved through a negative power. It means that at large distances, the MFPT is going to saturate with the distance. In other words, you lose the memory of the initial position. In the opposite case of compact exploration, this time this parameter is involved through a positive power. In this case, initial position always matters. And in between, you have this marginal case. This asymptotics theory actually is applicable to representative model of statistical physics, like transport in disordered media, fractals, and anomalous diffusion. I just would like to quickly illustrate it by considering two examples.
Just 1 second.
Sure.
Can you clarify, R here represents the distance
Yeah, R.
on the graph, right?
Yeah, exactly.
Okay.
If it is a graph, yes, on the graph. Okay, so the first example I would like to consider is simply the case of a 3D simple random walk. So in this case, this is a simple random walk, so dW is equal to 2. This is regular diffusion. Regular space, dF is equal to 3. So we are well in the non-compact exploration regime. And this is a plot of the MFPT reduced by the size of the system as a function of a source target distance. In red, we have the numerical simulations, and in blue, the approximate MFPT. So you can see two things. First, the good agreement between both. And second, the saturation effect with the distance I mentioned previously. The second examples I wanted to consider is the same problem, but now in a crowded environment that would be described as a critical percolation cluster. In this case, it is known that dW is greater than dF. We are in the compact exploration regime. And this is again a plot of the reduced MFPT as a function of the source target distance, this time in log-log plots. So each color corresponds here to a different size of the system. So you can observe a good data collapse onto the theoretical master curve. So finally, in the case of a Markovian process, we have a very simple way to extract the dependency on the geometrical parameters of the MFPT. Actually, you can do exactly the same to determine all the moments of the distribution, but today I will present only results for the MFPT. Yeah, sure.
In this case, you are actually first taking the n-volume limit, keeping R fixed,
Yeah.
and then looking at the large R.
From the point of view of the analysis, exactly. But in the numerical simulation, of course, this is not the question.
No, I'm saying that if R also scales to n.
Yeah. Exactly. It's a difference. It's a very important point. Very important point. Absolutely. Absolutely.
But then you can also say something in that.
Yeah, it works. Actually, you can determine the correct scaling for the global mean first passage time, for instance, which is obtained by averaging over all the points of the DOM. Other questions? So now, this was true for Markovian processes. The question now, what can be said for non-Markovian processes? So the first example I would like to consider concerns the case of a polymeric Roos chain with a single reactive monomer. So exactly the same problem in confinement, still reflecting. We have a single target, and we have this single monomer able to find the target. So first, let me remind you what is the Roos dynamics. A Roos chain can be defined as a chain of n phantom Brownian particles connected by springs, and here we have a single reactive monomer. So of course, the global evolution of the chain is still Markovian, but the evolution of the only degree of freedom associated to this reactive monomer is not Markovian anymore, because its evolution depends on the whole configuration of the chain at a given time. So finally, L1 is a non-Markovian variable. However, we can try to repeat the methodology we developed before. So the idea, of course, in this step 1 is still to try to obtain a renewal equation, but now applying the formalism to the full conformation of the polymer. So we start from an initial conformation of the polymer. We consider a final conformation with the reactive monomer inside the target, and we can still classify all the trajectories leading from this one to this final conformation as the function of the first time the reactive monomer crossed the target. We can do that, but we need to keep track on the memory of the position of the other monomers at the very time of the reaction. If you do that, you can write this renewal equation, this ket notation denoting the set of all the positions of the monomer of the chain. So you can still sum over all the possible realization of the first passage time. This is still a convolution. You can still go to Laplace domain, small Laplace variable limit, and you obtain an exact expression for the MFPT, which involves this P function, which is a kind of effective propagator. Here, P conditioned by pi is defined as a kind of average over the distribution of the polymer conformation at reaction, as we just said. So at this stage, we are facing two difficulties. We are still in confinement, first difficulty. This difficulty we know now how to overcome. It is enough to go to the large volume asymptotics after having rescaled everything by V. So now we are back to these propagators in the absence of confinement. But we are now facing a huge difficulty, the fact that these propagators involve the distribution of the polymer conformation at reaction pi. Question, how to go further? So what we did is to rely on approximations for pi. The first approximation you can imagine, the simplest one I guess, consists in assuming that all variables relax instantaneously to an equilibrium distribution. In other words, pi is given by the equilibrium distribution of the Rose chain, which is a Gaussian distribution. As I will show you in the next slide, this leads to quantitatively inaccurate MFPTs. A slightly more involved approximation you can imagine consists in assuming that pi is still a Gaussian, but this time with unknown means and unknown covariances. Actually, you can obtain from previous equations self-consistency equations satisfied by these unknowns. You can solve them numerically, and you obtain an expression for the MFPT. I don't have time to present them in detail, just would like to show you the comparison with numerical simulations. So this is a comparison between the Markovian theory in green, the non-Markovian theory in red, and numerical simulations denoted by symbols in 1D and 3D. Still a plot of the reduced MFPT as a function of the source target distance. So in both cases, you can see that there is a good agreement between the non-Markovian theory and the numerical simulations. And second, that the Markovian theory overestimates the MFPT. And this is a general trend. Actually, you can understand this last point because as a byproduct of the analysis, we also determined the distribution of the conformations of the polymer at reaction. This is what I called pi previously. And this is a typical conformation we obtained from this non-Markovian theory. And this is typically an elongated conformation to be compared to an equilibrium conformation. So now we understand that at the moment of reaction, the polymer is actually elongated. In turn, it means that you have a larger effective reaction radius than in the Markovian theory, and this leads to faster kinetics than in the case of Markovian theory.
Excuse me, could you tell a little bit more about the model? Because I'm lost here.
Yeah.
Are you talking about particles with central forces?
No central forces, springs.
What springs?
Spring.
Okay, but springs are just central, depend on the distance between the elements.
Absolutely,
right?
absolutely. Yeah.
Right, this is what I call central.
Okay, sorry.
And it's just a one-dimensional chain.
No, 1D, 2D, 3D in principle.
No. They can move, but particles are connected.
Okay. Absolutely, yeah. Yeah. Okay. The model is clear? So in this example of non-Markovian process, you are able to develop an approximate theory for determining the MFPT. In this case, we were able to identify all the degrees of freedom responsible for the non-Markovian feature of the motion. In practice, this is not the case. In practice, you have access typically to the MSD of a given single trajectory, for instance. And by definition, you do not have access to the hidden degrees of freedom. So the question now, we consider a Gaussian process with stationary increments, and we know only the MSD, which is enough to characterize this process. Are we able to say something about the MFPT? So we try to repeat the methodology we are now familiar with. So the first step consists in trying to write a generalized renewal equation for that problem. So I denote here the 1-point BDF by P, the first passage time density by F, and to make things simple, I write this in 1D by assuming that the target is in 0. So the renewal equation consists in writing P0 at time t by summing over all possible realization of the first time 0 is reached. So in red, we have this first visit contribution, exactly as before. And in green, we demand that the random walker comes back to the same point. But now, we are in the non-Markovian case. We need to keep track of the FPT. This is what is written here. We need to keep track of the memory of the FPT. Previously, we could forget everything about that. Now, we have to keep track of it. But this is exact, strictly speaking. Complicated, but exact. We do the same as before. We can obtain an exact expression for the MFPT that involves this quantity Q pi. Q pi is defined this way formally. It is actually the probability for being on the target at a time t in the future of the FPT. So what is this object, the process in the future of the FPT? Just to make things clear, let us represent several runs of numerical simulations. The red arrow corresponds to the FPT, a random variable. And here, we check the FPT at the new origin of times. So if we do that, we obtain this green contribution, which is the trajectories in the future of the FPT. Of course, you can do statistics of this object. For instance, you can determine the average trajectory in the future of the FPT. This is what you obtain. A key observation of numerical simulations is that actually the PDFs of this process in the future of the FPT are almost indistinguishable from Gaussian histograms. And this is reminiscent of what we did in the case of the rose chain. We're going to assume that the process in the future of the FPT is a Gaussian process. So now we repeat step 2 and step 3. Step 2, we get rid of the confinement by going to the large volume asymptotics. Step 3, we use this Gaussian approximation. And if we do that, it is very easy to write the MFPT this way. It involves, this is written in 1D here, x0 is the initial position, psi of t, this is the input in the model, the MSD, and we have this mu of t, which is the average of the process in the future of the FPT. Importantly, you can obtain an equation satisfied by this unknown. And finally, we have done exactly what we wanted to. We have related the MFPT to the MSD only. A comment, I find it quite strange that what is involved here is a mean future trajectory, not the mean past trajectory, just a small comment, but we were very surprised initially by this observation. Another comment, it is very easy to define a Markovian approximation starting from this expression. Markovian approximation will be defined by taking mu of t equal to 0. Once you reach the target, in average, you stay on the target. And last point, importantly, you can show that this theory is actually exact at order epsilon square, where epsilon is defined as a measure of the non-Markovianity of the process. Now, I just would like to illustrate what happens when you are not close to a Markovian process. So I will consider two examples. First, the case of a one-time scale model, very simple model, in which you are diffusive at small times. You are again diffusive at large times, but not with the same diffusion coefficient. This is a model used in several contexts. So very simple model involving only diffusion. You can apply the general theory. This is a comparison both of non-Markovian and Markovian theory with the numerical simulations, still a plot of the reduced MFPT as a function of the distance in 1D, 2D, and 3D. And you see a very good agreement with the numerical simulations. And you can see, and I find it quite surprising, that even for this very simple case, you have an effect of non-Markovianity, even if it is diffusive at small and long times. So second example, an example involving a kind of infinite number of time scales, fractional Brownian motion, defined by its MSD and involved in a variety of contexts. In this case, the model displays long-range correlated increments. This is easily seen by taking the double derivatives of the MSD. If you do that, you obtain this correlation between the increments. This is algebraically correlated, and the sign depends on the value of the Hurst exponent h. You obtain that if h is greater than 1/2, you have persistent superdiffusion. If h is equal to 0, a regular diffusion. And if h is smaller than 1/2, anti-persistent subdiffusion. So typical path associated to what we said. And the comparison of the theory and the numerical simulation in this case for 1D, subdiffusive and superdiffusive, and for 2D. So again, we observe a good agreement of the non-Markovian theory, at least at small distances, which is expected because this is a large volume expansion. And in this case, you can see that the non-Markovian theory, but it can be defined, is very, very different from the Markovian theory. So we have excellent agreement between both. And in this case, we really see quantitative memory effects. So finally, for Gaussian processes, we are able to develop a theory which is approximate and exact when you are close to Markovianity. We have shown that you have quantitative memory effects. And now I would like to ask additional questions. First, memory is important. Is it important enough to modify the very scaling of the MFPTs that we obtained in the Markovian case? Second question, we have discussed only the mean. What can be said about the scaling of the full distribution? And finally, is there a potential effect of aging in the system? Up to now, the increments were assumed to be stationary. So now we consider the MSD defined this way, and I call alpha the aging exponent in the system. So t is the time you start to make the measurement in the system. So I just would like to give you the analysis you can give in the case of the compact situation. And this now is going to apply only on scaling arguments. So the first point consists in separating direct and indirect trajectories depending on the following facts. Is the target reached before the boundary or the opposites? So I call 1 minus pi the probability for the target to be reached before the boundary. And ft is a conditional probability to reach the target at time t for the first time, knowing that it is reached before the boundary, and similar definition for fb. Actually, the weight can be estimated by adapting exactly the method developed by Satya and Alberto. This is exactly what they do in the one-dimensional case, but the argument is very general. You can do the following thing. 1 minus pi, by definition, is the time integral of the first passage time on the target t. And now they do the very interesting remark, which is the following. Most of the trajectories involved in this sum actually corresponds to trajectories reaching the target before the boundary, meaning that it is done at a time scale which is smaller than the typical time scales involved to reach the boundary. By definition, this time scale is big R at the power dW. And second remark, at this time scale, you can replace f by f infinity, as if there was no confinement. If you do that, if you use scale invariance, by definition this, if you use the definition of the persistent exponent, you finally obtain this very general expression for the weight pi. And this is true actually as soon as the process is compact. Interestingly, you can extend this idea to the determination of the other quantities involved in this expression. You can obtain this scaling expression for ft and this one for fb. And finally, if you sum up everything together, you make two interesting remarks. First, the fact that direct and indirect trajectories are exactly the same weight in the large volume limit. And second, you can show that this scale variable, the time t divided by capital R at the power dw, is distributed with distribution. This one is a geometrical factor, and this one depends only on h. And from this, you can obtain everything. In the case where the MFPT is defined, you obtain in particular the MFPT, and you obtain this general expression of the MFPT as a function of the geometrical parameters. So here, I remind you, dW is a work dimension, theta is a persistent exponent. So several comments. First, what can be said in the case we considered previously, where the increments are stationary? In this case, actually, you can argue that theta is given by 1 minus df divided by dw. If you plot this in this formula, you finally re-obtain the scaling we obtained in the Markovian case. So finally, this scaling is very robust. It is true also for highly non-Markovian processes as soon as the increments are stationary. For instance, it is true for the fractional Brownian motion. Second point, when the increments are not stationary, you obtain an MFPT that is not linear with the volume anymore. It can be sub or superlinear depending on the problem. This is a comparison with numerical simulations for a variety of examples involving, for instance, random acceleration process, fractional Brownian motion, but with non-equilibrated initial condition, and in each case, you recover the behavior predicted by the theory. You can do the same in the non-compact, what you can do at the level of the full distribution. I have no time to present it, but in each case, you obtain a very good data collapse on the theoretical master curve, even if you do not know the precise form of the scaled distribution. You can do the same in the non-compact case. The key point now consists in summing how many times you miss the target before finding it. This is very different mechanism as opposed to the compact case, but you're able to count this number. And finally, you end up with the fact that this random variable, t divided by capital R to the power dw, divided by this term, capital R is associated to the length of the confinement, small a is the length of the target, and you have this extra factor. Psi is defined on the next slide. Psi is defined as a function of df, dw, and the aging exponent. And finally, in the case of the MFPT, when it exists, you obtain this general expression. Again, when the increments are stationary, here in the non-compact case, it is enough that they are not stationary only at long time, but in this case, it means alpha equal to 0, and you recover the Markovian scaling. Again, even for non-Markovian processes, it is true as soon that the increments are stationary in the long time. Otherwise, you can obtain sub or superlinear scalings of the MFPT with the volume. And this is a comparison with numerical simulations. So to conclude, we have considered the following problem. The problem of a target of radius a in a confining domain. You start from a distance r, and you assume that you know the MSD. Potentially, you can have hedging in the problem. You are interested in the MFPT. What can be said? In the absence of hedging, we have shown that this scaling obtained in the Markovian case is actually very robust. It is still true. And in the case of a Gaussian process, you can actually determine the number. This is complicated, but you can obtain an approximate expression for this number. If now you have aging, the MFPT typically is not linear with the volume anymore. In turn, this non-linearity of the MFPT could be a kind of hallmark of aging. Just would like now to try to draw very simple conclusions in the problem of reactivity in confined media like cells. First question that we asked in the introduction, finally, is the initial position an important parameter of kinetics in confinement? As we've seen, all depends on the nature of the exploration, compact or not. In the non-compact exploration, typically regular diffusion in a medium that is dilate enough, we have seen that the MFPT in this case saturates with the distance. In other words, finally, in this case, the initial position does not really matter because you lose the memory of it. If now you consider the same problem but in a crowded medium described as a critical percolation cluster, this time the initial position is a key parameter and the MFPT strongly depends on it. This time the reaction is not only diffusion limited, it is actually geometrically controlled. And second question, I really do not really have time to discuss it today. What can be said about the variability of the reaction time? Again, all depends on the nature of the exploration. In non-compact cases, you can show that actually there is a single time scale involved in the problem. In turn, it means that the reduced variance is a bounded function of the volume. Even for very large volumes, this quantity remains finite. For compact cases, it's very different. We have many time scales involved in the problem, and the reduced variance can be very, very large if you start close to the target. You can obtain giant fluctuations in this case. So I just would like to conclude by thanking again my collaborators and by thanking you for your attention.
Thank you. Question?
Is it true that this analysis is applicable only when the target is inside the domain, so you can put it on the boundary?
Strictly speaking, what we have done, but actually, if the target is close to the boundary, the scaling is not modified first, and instead of using in the limit the free propagator, you can use the propagator close to a target, typically by using an image method.
In principle, it can apply to narrow escape.
So you cannot obtain the detail and the refined structure of the narrow escape problem, but you can take a target close to the boundary.
You went very fast in your presentation, so I'm not sure I followed all the details. Many years ago, when we looked at the following question, we had a polymer, we had a target on the boundary, and we were actually interested in what is the first time for one of the monomer to hit this target. And so we realized that this question was actually harder than what we thought, because when the polymer arrived to the small hole, so let's assume that you have reflecting boundary condition except locally, most of the monomers that are not the key one, let's say the monomer, there's only one that can be absorbed. The rest, they are reflecting.
Only one can react with...
Only one can react.
Exactly as here.
So then here is what we observe, and I'm not sure we were able to calculate ultimately. Many of them are going to hit the boundary first, and then they are going to repel the entire polymer before the crucial one was able to approach even closer enough to hit. And so this, because you have this chain, this created some kind of effective repulsion well, because they reflect. So some they arrive, they start to be reflected. Many are starting to be reflected, and the one that is, so this one can be either at the extremity or in the middle, and this was important. Then the guy cannot go, and then we started to look at how we can estimate the mean first passage time. I mean, the first time for this one to go, it was very hard, because to estimate this effective potential, we could not do. Have you encountered this kind of situation, and were you able to do something in this kind of direction?
Two elements in your question, I think. First, effectively, the reactive monomer is not necessarily at one extremity of the chain. And this we can account. It does not induce major changes even in the result, quantitatively. I mean. But you can do everything.
It changes the result.
It changes the number, yeah.
It changes the mean first passage time.
Yeah, the number, I agree. But we can do that. The other element of the question, what happens if the target is on the boundary? This we have not investigated in detail. In principle, I would expect that it should be doable, but if you describe the effects that are that subtle, I'm not sure we can describe them.
I think maybe to follow up, I think it means instead of the Rouse chain, if you use a real chain that cannot penetrate and you have real interaction in the chain, I think that's what he means, then the results might be very different.
This I agree, yeah. And we do not know how to do that. Yeah.
So you have a phantom chain.
Yeah, phantom chain.
Effects are not related.
Absolutely.
Any more questions?
Yeah, when you approximate the trajectory in the future of the first passage, sorry. So you do this Gaussian approximation, which I think works well for Gaussian process. Okay. But then how do you determine this? I mean, the parameter of your Gaussian distribution?
I've written one of the equations. It is. You mean technically? How do you obtain this equation?
How? Yeah, exactly. I mean, how?
It is
how do
obtained
you
actually by considering a kind of refined renewal equation. The renewal equation, you're interested only in the probability to be on 0 at time t. But you can also do the same for joint probability, to be at 0 at time t and to be at another point at another time. And by doing so, you can obtain another equation for this unknown.
Assuming this renewal type of...
Exactly.
If there are no more questions, let's thank the speaker again.
Okay, so first of all, I'd like to thank the organizers for inviting us all to such a beautiful venue. And the sun is shining, so what more could one want? And today I'm going to talk about stochastic resetting. The actual title in the program was a non-Markovian resetting, but I'll get onto that. I'll just say that in the last few years there's been quite a lot of activity in stochastic resetting, and a number of the active players are in the audience, so I'll try and give credit where credit's due. And I've tried to update my talk to take into account some recent developments. But nevertheless, I think it's still useful to start the talk in the way I usually do, to give to set the scene and capture the idea in a nutshell. So I'd like to think about my, I've actually moved now, but I used to live in a flat in Edinburgh. So a flat is an apartment in Edinburgh. A tenement's a sort of good solid apartment building, Victorian. And in my apartment, I had a good front door, good solid front door. And next to the door, there was a hook where the idea was I would leave my keys. And below the hook, there was a table with unopened letters, etc., and various junk. So often in the morning, I would be going to work, and I would go to the hook by the front door where the key should be, and of course, the keys were never there. So then I would look on this table underneath the hook, keys not there, and then I would go into the kitchen and look around a bit there, and then maybe go into the front room. And at some point, I would say to myself, well, what am I doing here? Because getting older and memory is not so good. And I would say, yeah, okay, I'm looking for my keys. I'm not finding them, so what should I do? And one idea is perfectly natural, is to say, okay, let's just start again and go back to where the keys should be, which is on the hook by the door. So I would, if you like, restart my search, or go back to the beginning and start again. And the question is that a good strategy, and can one show that's a good strategy? So that's the basic idea. And in this talk, what I'll be thinking about is me searching around, shuffling around is like some kind of stochastic process, a local stochastic process such as diffusion. And the going back to the starting point is a process I'll call resetting. Okay. Is it working? No. Never mind. So this idea of the general idea of search problems, and this idea of short-range moves mixed with a long-range move, is quite ubiquitous. So it is genuinely, there is a theory of foraging about how animals find food, and the idea is that there's some short-range move where the flock forages, which is like diffusion, and then every once in a while the flock will up sticks, or the herd of animals up sticks and go somewhere else completely different. So that's sort of like a long-range resetting. And this idea of a mixture of short-range moves and long-range moves is known as an intermittent search strategy. And there's a number of people in the audience who have worked on this extensively, so Olivier, Bénichou, and Ralph Metzler, and Gleb Shannon. So also that applies to biomolecules that are looking for some binding sites. So say in simplified terms, a protein is coming down onto DNA. It can bind and then make local moves along the DNA looking for a binding site, or it can unbind and then start again somewhere else. And it appears that a mixture of the short-range moves and the long-range moves is a good strategy. So that's the idea. The question I asked at the beginning, how does one search for lost keys and then go back to where they should be? That could be a good strategy. And more generally, the idea is that if one thinks of the search, so me looking for the keys as some stochastic process, or else if you think of some stochastic computer algorithm trying to do something, if it's sort of getting stuck and taking a long time, so that would be like me looking for my keys and wandering out the front door, say, and going down the street. I'm not going to find the keys there. But if I did that, it would take a long time for me to come back by local moves. And in fact, it's better to do the reset to start the process again, to shortcut these long time tails in the time distribution to do a task. So that'd be like if you have your computer algorithm, it's some stochastic algorithm, it's kind of got stuck and is not finding a solution. Better just to start again, switch off the computer, start again, then wait for it to find a solution. So that's the general idea. So what I'm going to start with is, as I mentioned, I'll start with the idea of as the local stochastic process being a diffusive process and show how resetting can fundamentally change its properties. Then I want to go on to a more general formulation that a lot of people have been working on recently, which we'll call the renewal approach, and to show that if you use this approach, you get results quickly and see the generality. And then at the end, hopefully we'll discuss some recent developments, the non-Markovian resetting, what I call phase space resetting, and not just resetting to the initial position, but resetting to somewhere along the trajectory. Okay, so let me start off with diffusion. So, did he take away the thing completely? Okay, but it's not working for. Yeah. Okay. Yeah. So this is a usual diffusion equation, right? Simple enough, and x is the position. So p is the probability density of being at x at time t, having started from x naught. So that's simple and familiar enough. So the resetting is, so the way I'm doing it, it's a resetting with a constant, here at least. What I call Poissonian resetting is resetting with a constant rate r. So I lose probability from point x, and then it goes back to the resetting position. And for this talk, I'll make life simple, and the initial position of the particle is the same as the resetting position. So I get a plus term there from going back to the resetting position. So that's how you modify the diffusion equation. Then one can actually solve this. Let's just consider the stationary state when t goes to infinity, and this term goes to 0. Then you can solve this equation. There's no p. No, there's no p. There's no p. You could write it as an integral over the right. So the probability, it's a fair question. The probability is coming from everywhere, but because probability is conserved, the integral is 1. So that's actually, you could put an integral of all the probability there, but it's just 1. And it's true, in a moment when we have survival probability, we do need a term there.
For mortal particles, there would be
yes, there would. Yes, that's right. No, good point. Okay. Yeah, so you can solve this and you get this distribution. So it's a double exponential decay, which is known as Laplace distribution. And okay, the first thing to know is that this was diffusion. If I didn't have resetting, there's no stationary state. The Gaussian just gets broader and wider. So the first thing is the resetting induces a stationary state. Second thing is it's a non-equilibrium stationary state, by which I mean that there's constantly resetting, which leads to a probability of current of probability from anywhere out here back to the resetting position at x naught. So there's a circulation of probability, so we call it a non-equilibrium stationary state. So resetting is a simple way of generating non-equilibrium stationary state. So that's all simple enough. What I want to do now is to show how you can get that very quickly and more generally by what I call renewal approach. So this approach actually it's kind of come up a lot of times in the literature. I mentioned these two papers as probably the first, I think, places that it was studied, but it's quite general for these kind of stochastic mean first passage time problems to introduce a renewal approach, as we saw this morning in Olivier's talk. So first of all, I want to consider last renewal equation. So the idea here is you think of the last time there was a reset. Now, it might be that there was no reset. So I'm thinking about the probability density to get to x from x naught. So if there were no resets, and because it's a Poisson process, the probability of no resets is e to the minus RT. Then in fact, the probability of getting there is just what we'll call the propagator. So the R there means there's resetting. The 0 here means that it's the probability of going from x naught to x without any resetting. So that's the propagator. So that's the case when there's no resets. Now, if there have been one or more resets, let's think about the last reset. And the probability that the last reset happened at time t minus t primed is r. Okay, and then we need, because we're at time t, we need no resets to have occurred from in time t primed. So I get that term for the probability that the last reset was at t minus t primed. And then I need to get, no? Is it working? Oh, okay. It is. Thank you. Yeah. And so this is the last reset is at t minus t primed. And then it needs to get in time t prime from x0 to x without resetting. So the advantage of this is that all this tough stuff on the right-hand side is p0, so it's a propagator that you already know. Yeah.
Small question. It has nothing to do with diffusion equation, Wiener process,
No.
whatsoever. It's other process.
Yes. Okay. It's not. It doesn't have. To, it's not. Certainly, it's not restricted to diffusion. I have to. Okay. I have to think about how arbitrary it is, but it's pretty arbitrary. Yeah.
Oh, it's totally
Totally arbitrary.
arbitrary.
Okay.
It holds even for non-markov.
Yeah. Okay. Well, I'll come to that in a moment, or later on. So that's the last renewal. Yeah, so as I said, this is nice and simple because all these terms are p0, and then actually I can just get the stationary state by letting t goes to infinity. Then this term disappears, and then this you'll recognize as basically a Laplace transform with Laplace variable r. So actually the stationary state is the Laplace transform of the process without resetting. And for those of you who are expert, you'll remember that the Laplace transform of a Gaussian is actually that Laplace distribution. So that's last renewal equation. You can also do first renewal equation. So the idea here is you think about when the first reset occurred. So again, there may have been no resets, so you get the same term there. Or the first reset could have occurred at t primed. So here it occurred at t, so that was the last at t minus t primed. Here the first is at t primed. So again, you get that same probability of the first resetting occurring at t primed. But then there can be as many resets as you like, so it's PR this time, and going from x0 to x in times t minus t prime. So at first sight, these two equations look different because this term is different from this term, but you can check that it actually gives the same solution. And the simplest way to check if you want to is to take the Laplace transform of the equations, you get the same thing. Or else just solve them, you'll get the same solution. Right, so that's last renewal, first renewal. And as I said, when you can use last renewal, it's simpler because it just involves quantities that without resetting. So it just involves the propagator of your process. Okay. So now I want to move on to considering, we've got our process. We can think, for example, a diffusive process, it's resetting, and we want to find a target. And the simple way of modeling this is to have the target at the origin and to make the target absorbing. So it's like having absorbing boundary problem at the origin, and we heard a lot about those problems this morning. So what I want to consider is the survival probability. So here, the variable x0 is the initial position. So I'm integrating over it can end up wherever it wants as long as it hasn't touched the origin, so it's survived. So it implies an integral over final position. So the arguments are it survived for time t having started from x0. And again, we can write, I'll just write the last renewal equation here. So the first term is that there's been no resets. So basically, it's the survival probability without reset, which I'll write as Q0. And then I can say, the last reset was at t minus t primed. So it had to survive with resetting up to t minus t primed. Then the last reset was at t minus t primed, so it's got t primed to survive without resetting. So there's a 0 there. So it's very simple to write. Once you've got the hang of it, you can just write down that equation. It's very general. And then it's very easy to solve. You just take Laplace transform of that. Then because of that, it's because of the e to the minus rt, it's Laplace transform with Laplace variable r plus s. Sorry, I should have said it's usual Laplace transform, so s is the usual Laplace variable. Then this is just a convolution, so I just get a product. And then just within 2 lines, I can immediately write down the answer for the Laplace transform of the survival probability in the resetting process. And it's just in terms of the the process without resetting. So then I can take whatever process I want and substitute in. And in particular, I will look at the diffusive process. So this is nice and general and simple. Then, well, one thing to focus on with the Laplace transform, the survival probability, it's kind of well-known result. If you just set s equals 0, the Laplace variable 0, then you get the mean time to absorption, or equivalently, well, I call it here the mean first passage time to the origin. So it's just the mean time for this particle to get absorbed, or the mean time for the searcher to find the target at the origin. So all I need to do is to put s equals 0 in the previous expression. So here I'm going to just focus on the diffusive case. I won't give you all the formulas, but in the diffusive case, what the answer comes out as this, which is quite simple. But what I want to just illustrate is that clearly as r goes to 0, so the resetting goes to 0, this mean time, mean first passage time, diverges. And that's entirely expected, because for a diffusive process, you know that came up again this morning, that the mean time to basically to get to a particular point diverges, because you can go off in the wrong direction and it takes a long time to return. So that's like me searching for my keys and wandering off down the street. Takes a long time to come back, so the mean time to get to the keys if I don't reset will be infinite. And also, you can see that it diverges when r goes to infinity. And that's because if you're resetting too frequently, the particle never gets a chance to get anywhere, because it keeps getting put back. So again, it will never get to the origin. And in between there, there's a minimum at some r star. And it's easy, it's just basic algebra to work out, or calculus, to extremize this function and work out the minimum. So if you set dt by dr equals 0, you get this simple transcendental equation involving y. So what is y? It turns out it's this combination, x naught times r over d to the half. And that's actually, you interpret that as a ratio of two lengths. So x naught is clearly the length from the resetting position to the origin where the target is. And this length is actually the typical distance diffused between resets. So you can think about that as that's what it is. So that when that ratio is 1.5, this you satisfy this equation and you find the minimum. So that's a sort of interesting result. On the other hand, you could argue that, well, that's all very well. It shows there's an optimal resetting rate, but you only know what the optimum is if you know how far the resetting site is from the target. So somehow you need to know some information about your target to tune your resetting rate. But nevertheless, the principle is there that there is an optimal resetting rate.
You count for the time of the reset?
You can, yeah. Okay, there's been a couple, yeah. That has been addressed recently. So you can put a time penalty in. So actually the first person to do this is Shlomi Ruveni, and it's straightforward enough. We've also done it, and we call it refractory period. And yeah, the calculations are a little bit more complicated. But I can tell you about that if you like later. Yeah. Okay, so that shows there's an optimal R. I also just want to mention, because I quite like this, that from the Laplace transform or the survival probability, you can also, the other thing that you can do is to extract the large time behavior of the survival probability. It's very difficult to invert the Laplace transform generally, but as usual, you can extract the large time behavior by looking at the analytic structure. So again, this is for the diffusive case where I've put in the formulas. I've got this, and I look for the singularities, and that will occur when there's a pole, which is when the denominator vanishes, and so I get this formula for S naught. Now in the case where, oh, that's not so good. Yep. So in the case where this variable y, those ratio of those two lengths is very large, then you see that S naught will be very small, and if S naught is small, you get this explicit formula for S naught. And so then that's where the pole is, so the large time behavior of Q will be e to the minus, e to that times t, so I end up with this for the large time behavior of the survival probability. And that's interesting, so it's exponential, but it's actually a minus exponential of a minus exponential. So this came up in, I think, yesterday's talks. It's a Gumbel, of the form of a Gumbel distribution, which is a cumulative distribution in extreme value statistics, for that the maximum of a bunch of random variables is less than something. So you might ask, well, why does this Gumbel distribution appear? And it's actually quite a simple argument and for why that is so. So basically, and it comes down to this renewal idea. So I should have drawn this picture earlier. We've got the origin is where the target is, and this is our resetting position. So we started off here, and there's some, in the diffusive case, it maybe diffuses out there, then gets reset, and then it goes this way and gets reset. And we have these independent renewals. Once it's renewed, it doesn't remember the past, they're independent. And for the process to survive, through each of these renewals, the furthest distance to the left must be less than x naught. So if you think of the distance to the left as a random variable, then the random variable is independent for each of these renewals and must be less than something in all of them. And that's just exactly what you need for a Gumbel distribution. There is a slight subtlety here. To get the mapping exact, you have to, the average number of renewals is r times t, because r is the rate. And actually, to get the calculations to match up, you have to consider the fluctuations in the number of resets. But I don't want to get into that detail. Anyway, that's where Gumbel distribution appears from. And that's just the explanation I just gave you in words. So let me crack on. What I want to move on to now is the case of non-Markovian resetting. So far, we've considered just a resetting rate, a constant rate r, which is a Poisson process. When the bell rings, we reset. Now, there was a number of papers that actually came out about the same time that considered the case of really when it's non-Markovian or non-Poissonian. And the way we did it with Arnab and Anupam was we were interested in a reset rate r that depended on the time since the last reset. So because it needs to remember when the last reset was, it becomes non-Markovian. And that's actually equivalent, more or less, to considering just a waiting time distribution between resets. But the reason we were interested in this formulation, we were thinking that, so there's some resetting, remember, is probability per unit time of resetting rate is probability per unit time of resetting. So we were thinking that if nothing has happened, the search hasn't been completed, and it's been a long time, then you want to increase the resetting rate. You want to give a higher probability of starting again. So we're really thinking of increasing functions of time for r. Yeah. I would say it's not Markovian because it needs to know the past. But you're saying not Markovian, but not. I would say it's not Markovian. You have trouble writing down like a Fokker-Planck equation. You have to do some clever stuff to do it. So I would say it's non-Markovian. That's because of the way we've chosen it. We have chosen a rate. So the probability of no reset up to time t is then given by exponential minus rt, where r is just the integral of little r. So that's the convenience of this form, and it gives nice expressions for the probability of no reset up to time t and the probability density for the first reset. Yeah.
But I would sort of
You side with him.
Yeah, I side with him in the sense that you can write down the Fokker-Planck equation, it will be time dependent actually, but it's still a Markov process.
Yeah, I think it will be
It's a Markov process, but it's a time dependent rate.
Okay, so that's really what he said. Okay. Okay, so I should maybe just cross this out and put non-Poissonian or non-homogeneous Poissonian. Or non-homogeneous Poissonian. Okay. Right, so let me crack on. Again, it's easy to write the first renewal equations. So because of these probabilities have simple forms, this is again the contribution from trajectories where there's no resetting, and here the first reset is at time t primed. It's more difficult to write the last renewal equations. You have to think much more carefully, and it gets much trickier. But the first renewal is what we did, and these, again, are very easy to solve by Laplace transform, and you get the results. So I'm not going to bother you with all the details. What I'd just like to point out is some interesting results. So first of all, we wanted to investigate basically the case of increasing R. So let's say the rate increases linearly in time. So you can work out all these cases exactly, and indeed that will reduce the mean first passage time to the origin. And so we tried a few cases, and yeah, it reduces it. So then the question is, well, what's the best you can do? Like, what R of t can you choose that will optimize the mean first passage time? And what we concluded, when we were just thinking about the diffusive case, but we could show that, basically we proved that the optimal R of t was one that was, so this is the resetting rate, it was 0 up to some fixed time and then infinite. And if you think about it, what that means is that it's a deterministic reset period. So if you choose your reset period appropriately, then that will minimize the mean first passage time. So if you just reset deterministically after a fixed period. So that was our conclusion here. And it's recently been proven by Chechkin and Sokolov that this is indeed true for very generally. That so maybe Igor Sokolov will be speaking about this. So the idea is that if the reset can reduce the mean first passage time for your stochastic process, then if it can make any improvement, then the best improvement will be to have a deterministic reset of the appropriate period. And I think you can sort of believe that.
And the period is comparable to this period where you observe the minimum on that curve?
Yes.
Because from the units
comparable,
you
yes.
everything else, but probably the number is different.
The number is different. Okay, I haven't got the numbers. I haven't put the numbers up. Okay, so that's this non-homogeneous Poissonian resetting. What I want to talk about now is a recent thing that we've done with what we consider with Satya. So far, the resetting, we've thought of our stochastic process as being some spatial process, and we're resetting in space. And now we want to think of there being in a phase space where you have a position and a velocity or momentum variable. And we want to reset both the position and velocity and see what that does, just explore that possibility. So what we chose was a simple model that's becoming very popular in the active matter community. So the idea here is this is either called a run and tumble particle or a persistent random walker. And the idea is it's just a first order equation, so this is dx by dt is the velocity, but the stochasticity is in the velocity, so that's speed v0 times direction sigma, which is plus or minus 1. And then the definition of this model is that sigma flips with rate gamma. So the particle will go along a certain distance one way, then it will flip and go the other way. And you can work out various things such as the probability density. The interesting thing is that this is a simple model, but it goes, see, if you have gamma goes to 0, it never flips, it's ballistic. Whereas if gamma goes to infinity, then essentially it's a Wiener process, so it's just diffusion. So you go from diffusive to ballistic limits as you change gamma. So what we wanted to do was to add resetting to this process. Yes, it's Katz. Sometimes it's called Katz's model, but I would say that more common names are persistent random walker. He wrote one of the first papers on it, Katz. That's true. Okay. So we introduce resetting. So again, we just keep it simple. It's a Poisson resetting. So we're resetting with a certain rate. When a resetting event occurs, we reset the position as before. So position x goes to x naught. And then this was our velocity reset protocol. Remember, the velocity is sigma. The idea is we flip the velocity with a probability eta. So if eta is 0, we don't flip it, and it's position only resetting. And if eta equals a half, then essentially what you're doing, you flip the velocity with probability half. It stays the same with half. And effectively, you're randomizing as much as possible the velocity. So they're the extremes. That you don't reset the velocity as eta equals 0. You randomize it as eta equals a half. And then what we could do is work out the survival probability with the last renewal approach. But it's much more complicated because we had to consider joint survival velocity probabilities. So we had to consider survival probability given that we started with some velocity and that the joint probability of survival, sorry, I said it wrong. It's the joint probability of survival having started from some velocity sigma I and finishing with velocity sigma f. So all I want to say is that it's a much more complicated object, and because there's the sigmas are plus or minus 1, you've actually got a system of 4 survival probabilities. So there's a little bit of calculation to be done, but we could do it. And what we found is one could work out the stationary state. So first of all, no absorbing target at the origin, just working out the stationary state. Again, it's a Laplace distribution, so the double exponential distribution. And the width of that distribution depends on the gamma, the flipping rate here. And then the interesting thing is that, well, given that you start with the caveat that you need to start from symmetric initial conditions, eta doesn't enter into that at all. The velocity resetting doesn't affect the stationary distribution, which we found quite interesting. However, when we looked at the mean first passage time and survival probabilities, eta does come into it. And it turns out that velocity randomization reduces the mean first passage time. So again, randomly changing the velocity reduces the time to locate the origin. So I think that's what I want to say there. And the final generalization I want to consider was something done with Denis and Satya a year or two ago. So the motivation here actually comes from troops or herds of animals. So I think the example given was a troop of monkeys that explores new territory in the jungle. And then at evening, they want to go back somewhere to camp. So they choose somewhere they've been during the day to go back to. And then the next day, the process starts again. Similarly, I can think of myself trying to locate this center this morning. I don't have a very good sense of direction, so I had to come halfway and find the square and then try various possibilities. But I could remember where I'd been, so I went back to somewhere I'd been on my attempt to find this place and then started again. So the idea is that you need to have more memory. You don't just remember where you started, you have to remember all the positions along the way. Then the way we formulate it, we're going to consider just a diffusive process, and we're going to reset. And the idea is that we choose some time, so that we're at time t now, so we choose some torr that's less than t, the position, and we're going to go back to the position we were at time torr. So we have to define what we call a memory kernel, which is the probability of choosing time torr, given that we're at time t now. Then if you think about it, this is the diffusion equation. This is modified, again, we have a loss term from resetting here, and then a gain term into x, which we get to be reset to x. We have to choose some time torr, and it's the probability that we were at x at time tau that will contribute to the resetting to x. So we get this equation, which is linear in P. And okay, what we have to specify finally is the memory kernel. So in principle, it's a function of two variables, tau and t. So remember, tau is the present time, and t is the present time, and tau is the time we're going to reset to. And it's simplest to construct that from a single function, phi of tau. So we've got phi of tau, and it's just normalized correctly. So this kind of, you have to think about it a little bit. So if phi of tau is delta function at tau equals 0, then it means we always choose times 0. So it's the same as the resetting process I've discussed. We just go back to the beginning. If, on the other hand, phi of tau was very strongly increasing with tau, we would basically always choose times very recent in the past. So we wouldn't go back very far in the past. So it wouldn't have so much effect. But there's a whole range of phis that we could choose. And so we just wanted to explore the possibilities. So the first question to ask is, we know that when we reset back to the initial time, we generate a non-equilibrium stationary state. And what properties must phi have to generate a stationary state? And this is, remember, we're talking about diffusive process here. So it has to be weighted so that you prefer to go back to early times. And what one can show is that the distribution phi should decay with tau more quickly than 1 over tau. And then you get a stationary state, which one can calculate exactly in certain cases. Now, more interestingly, I think, is when you don't have a stationary state, then how does, so your distribution is going to grow in time, and how does the width grow? So one case that had been considered by Denis before was basically uniformly sampling the trajectory. So you pick uniformly, and that corresponds to phi, okay, this case here, where phi goes as t to the power alpha, and the uniform case is alpha equals 0. And then, in fact, you get a Gaussian, but the variance of the distribution grows like log t. So if you remember, usually with diffusion, the variance goes like t. So we recover the usual, sorry, I should maybe start with this case. We recover usual diffusion when this phi is strongly peaked at the present time. So it's a strongly increasing function of tau. So basically we reset to times very recent in the past. And then we just get usual diffusive behavior, perhaps with the diffusion constant renormalized. On the other hand, when we sample uniformly back in time where we've been, we end up with the variance going as log t. So it's a slow growth. And then in the marginal case, just before, you know, if phi decays any faster than this, then we get a stationary state. But in the marginal case, we can actually get log t behavior. So the width growing extremely, ultra slowly in time. So I find that quite fascinating that you can get all those behaviors just from one simple model just by varying the memory of, okay, or going back to places and sampling that you've been in the past, but sampling with a memory kernel that weights in a different way. So I think I'm about done. I'll just leave with a few, just try and summarize what I've said. So I've mainly just tried to set out the idea or the paradigm of resetting to show it's quite general, and to give some results on the particular case of a diffusive process. But more importantly, this renewal approach allows you to treat any old stochastic process. And what we've seen is that we can generate a mean first passage time when for diffusion, the mean first passage time is infinite without resetting, so you can improve the mean first passage time. And also the survival probability decays exponentially, as I showed. There's various connections with the themes of this meeting with statistics of extremes and renewal processes. Then the new things I haven't mentioned it there. The new things I discussed were the non-Markovian or inhomogeneous non-Poissonian resetting, and phase-space resetting, where we reset position and velocity. And finally, what I've called enduring memory, when you have to remember your whole trajectory and you reset to various points on it, can give different behavior from the usual diffusive behavior. Then there's a lot of things I haven't mentioned. I've concentrated here, the particular example I've used is 1D diffusion. You can study higher dimensional diffusion or other processes. The resetting rate can be made space dependent as well as time dependent, and then you can, if you want to study in more detail the search problem, instead of just having an absorbing target at the origin, you can say that the target is distributed according to some distribution. And all of these generalizations can be done fairly straightforwardly. And the final one was what somebody mentioned earlier. Is there a cost for resetting? And yes, you can implement a fixed or a distribution of costs for each reset. Okay, so I think I'll leave it there. You're welcome.
I have some questions because I know that sometimes I listen when you are at university. I see that.
Okay.
Je vois qu'en fait c'est un stochastic differential equation
Yes.
with a Gaussian noise and a Poissonian noise. In fact, it's a mixed. And by example,
I didn't understand. So the first thing you saw at university was an equation with.
finally, this resetting is a peculiar case of a stochastic differential equation.
Yes.
Where you have a Gaussian white noise and a Poissonian white noise.
For diffusion, yes. Yes, I agree.
And here is a very peculiar Poisson white noise, which is I reset towards one point.
Yes.
But by example, here when you begin to put R the xt, and when you begin to put these resetting distributions, then you enlarge your class of Poisson noise. You arrive in the class of kangaroo noise, where the rate depends on the initial state times the final state. And then you can imagine that a lot of things, not maybe a lot, but some things that you tell here remains true in a more general case, not of resetting, but of stochastic differential equation with Gaussian Poisson noise, with a peculiar Poissonian noise, as by example kangaroo noise.
I understand what you're saying. What were you calling that? Kolmogorov? Who noise?
No, he's calling kangaroo noise.
Kangaroo noise.
Kangaroo means just that the rates are factorized between the initial and the final state.
Yes. Okay.
And yeah, okay.
Okay, that's an interesting comment. Maybe I can discuss that with you a bit more.
Yes, okay. I think we can discuss after. Yeah, but if you add also the P, the X0. Yeah, but if you add the item 2 and the item 4. And slowly, also by example, yeah, I remember my question. Also here you don't put drift in your initial diffusion?
No.
So it was not very clear for me. By example, if you go in the circle, you can do resetting with just drift. Means it's a piecewise deterministic process. You don't need to have Gaussian noise. You don't need to have diffusion.
No.
You are in the circle, you drift with a constant drift you want, and then you reset sometimes. You come back to the initial point.
Yes,
then
you could do that.
Probably this will arrive to the... I don't know if the diffusion is really...
I didn't mention, certainly people have studied this, the resetting when you just have drift.
In compact?
On the circle, I don't know. So I agree, yes, you could do that.
Okay, thanks.
Yeah.
Okay. Just 1 second. Actually, have you looked at the high dimensional case when you have a small target and you reset, or this is just for the future?
No, we've worked out fully the diffusive case.
And you found some formula depending on the size of the target,
yes.
and
yes, you have to. So yeah.
Okay.
Of course, in higher dimension, you have to have a ball as your target. So we get different forms for the stationary state, because you have different types of singularities. To be honest, the resetting problem goes through fairly similarly. The calculation is more complicated, but it follows in the same way as the one-dimensional.
Yeah, sure. This I understand. This would not
Yes.
change. I have one comment.
Yeah.
It would be interesting to consider the case where you do not necessarily reset at one point, I mean in higher dimension, but you can reset on a piece of, let's say, a line, or
Yes.
that will have application in the context of accelerating Brownian simulations. Have you
Okay.
looked at this?
No, that certainly can be done. So in one dimension, yes, you can introduce a resetting distribution. So rather than having a point, you have some distribution for your resetting. So the problem that we looked at in another 2011 paper was how should you choose your resetting distribution to again minimize the mean time to find a target. So we thought of things like the target being fixed, and if you don't know where it is, how broad should your resetting distribution be? And there's various optimization problems there and some phase transitions in the solutions. So we studied that fairly extensively for diffusion in one dimension, but I think it could be extended to what you were saying, sort of lower dimensional spaces in the high dimensional diffusive space. You can do that. It hasn't been done, but I think it should work.
Probably related to what you said. My question is, the example that you gave involves consciousness.
Yeah. Well, I'm not very conscious in the morning, but
I'm trying to think of a microscopic process without consciousness that would involve resetting.
Do you have an answer to this?
This is sort of exactly what I wanted to ask. It seems to be that in the context of, say, cell biology, the more natural realization would be rather similar. If you have walkers that have a finite lifetime, so they can die at some point, and you have a source which sort of sends out.
Yes. Okay. So that.
So if those two rates are the same, then I think you're pretty much
yeah.
setting. And the question is, when does the first particle find the target?
Yes. That problem, just what you described, there's a guy called Gellenby who, that's the way he formulates the problem. But coming back to I think with the molecular binding, so Shlomi Ruveni likes the idea of Miklas-Menten reaction. So you think of some enzyme, it comes and binds, and then that starts off a whole chain reaction that may or may not produce a product. And by the enzyme, it will fluctuate and unbind and bind. That when it unbinds, it restarts the progress. So it's not thinking it's just chemical fluctuations. And that actually improves the time to produce the product because it stops chain reactions that are not going anywhere.
So I'd like to start by thanking the organizers, Gregory and David, for inviting me, and also the nice audience. So as you see, that title of this talk is quite very similar to the previous talk. So it's good that Martin has given a talk before me. So like many of the things I am going to talk in the beginning, it's a repetition of what he said. So I think it's a good that. Okay, so nevertheless, I'm going to go through it. Yeah. So I'm going to talk about some other aspects of this resetting, and let me just start by this thing. So this resetting, as Martin said, it's a part of a general problem called search problems. Okay, so and as you know that search problems are ubiquitous in nature, like searching for a misplaced key by Martin in the morning, or animals foraging, because usually animals, they when look for food, they do some kind of stochastic move, and that's another example of search problems. Then looking for solution for hard optimization problems, that's another kind of search problems. And this one is a similar one, like for example, if you want to look for the ground state of a glassy system, it's quite hard problem, and that's a search problem, and people have different strategies for this kind of search problems. Protein searching for binding sites on DNA, that's another search problems. And then for example, if you want to find your friend in the rock concert, I mean that's a search problem. So there it's quite ubiquitous, and in fact there is a special issue on the search problems where I think many of these people present in the audience, they have contributed to this issue. Okay, so I am not going to mention their name explicitly, but it's a nice volume, and like lot of you people have this thing. So a particular class of search problem is called intermittent search problem. So what you do is that you look for a target at some point, and after some point you relocate to a new position. So it consists of these two kinds of moves. So one is this target search, where you just look for the target. So this kind of search can be modeled by some kind of stochastic process, for example random walk or diffusion. And then there is a relocation move, so where you basically go from one position to the another position in a short amount of time. In this case, basically you don't do any search. Okay, these are the two moves. And for example, Bénichou has looked at this problem, and there is this nice review by him basically. So I encourage you to look at this review. Okay. So now this stochastic resetting problem, you can think of it as like a special case of this kind of intermittent search problem, where this relocation, so in this case relocation move is every time you just go to a new position, right? But instead of that, you can just think about it that this relocation move is to a fixed position. For simplicity, just assume that basically wherever you started from, you just relocate to new position. And you can just think of this position as your starting point, and for simplicity we assume that you just do it at a constant rate. It's like a Poisson process. If it is a continuous this thing, so it's a rate. Otherwise, if it is a discrete time, you can just think of it as a probability. Okay. So the rationale behind this kind of strategy is that sometimes, for example, if you are looking for a solution for a hard optimization problem, you searching for a long time and you don't find. So instead of keep on searching, it's just better to restart the whole process again. Okay. So this is the rationale behind this, and then there are examples you can cook up. For example, if you are just again looking, you are in a bunch of friends in Pisa and just going around, and you lost your friend, and you just reset to your most popular site, for example the Pisa Tower or something, because you hope that okay your friend might be there. Okay. So the foraging animals, again you can think of it like foraging is kind of a stochastic process, and once in a while these animals they go back to their nest. So that's like a reset, and then again you start the process once again. Okay. So this is kind of like a search with a reset. Okay. So let me just give a little bit of background. So it was actually there is a similar process studied by reset process studied by these people. So where they look at this multiplicative process. So where this n, so you change by this with a probability 1 minus q, and with a probability q you reset to a either fixed value. N of n0 of t can be a fixed value, or it can be a value assigned from some predefined set, and you just choose from some with some probability. Okay. So this is like a reset process for a multiplicative process. Okay. So then this another problem, it was mentioned in the comments of the previous talk. So there you assume that you have this search and they have a finite lifetime. So these guys they go and search for something, and then after some time they die. Okay. Okay, it's not a nice thing to think of, but okay, it happens. And then when the searcher dies, so you basically send a new searcher. Okay. So again, you can just cook up various possibilities where when the searcher dies, whether you send it immediately or you just wait for some time, but you can just think of it like this is a process. This process runs till the searcher dies, and then you reset the process. Okay. So this is your reset mechanism. So it's also studied in the context of optimization problem. Basically, if you are looking for, let's say, solution of a hard problem, and then you don't find the problem, and then once in a while you just restart it, and it seems that it's an efficient algorithm to actually find a solution for these hard optimization problems. Okay. So there's a simple model of this resetting introduced by Martin Evans and Satya Majumdar, which is an exactly solvable model, and I'm going to come back to this model later actually. So it's a very nice model where you can actually compute many of these things exactly as Martin has shown before. Okay. So various generalization of this simple model have been studied. For example, so in the first model, you always reset to a fixed point, but you can think that, okay, instead of resetting to a fixed point, you have a set of points, and basically you just choose these points from a certain probability distribution. Okay. You can also, this is what Martin has told, you can also have a time dependent resetting rate. Okay. Or you can also have a non-Markovian resetting protocol. For example, this basically the time distribution between this reset event is not exponential, but is some other distribution. Okay. But all these examples, the searcher doesn't remember the history of the path. Okay. So it of course remembers the initial point, but it doesn't remember the history. So these examples I am going to call, these are memoryless processes. Okay. So it doesn't remember how the system evolved, all the places the searcher has visited in the past. Okay. So there is another kind of processes which is called resetting with memory, and there is a nice problem actually solved by Denis and his collaborators. So what is the problem? So it's a random walk. So it does simple random walk, unbiased random walk, but with a certain probability. So it remembers all the site it has visited in the past, and with a certain probability it goes to the previously visited sites, and the probability that it goes to previously visited sites is proportional to the number of times the site was visited by the searcher before. Okay. So it's the more it visits a site, basically more likely to go back to that site, and it actually confines this thing a great deal, because if it doesn't have this memory, x square goes like t, but now it just evolves very slowly and it just goes like log t. And it seems that this model explains how these capuchin monkeys move in their home range. Okay. Various generalizations of this model have been considered, and there are some generalizations Martin has talked about in the previous talk. Okay. So I'm going to talk about another memory resetting with memory. So in this case, it can reset to any of the previously visited sites, but in the second model, what I'm going to talk is that it only remembers. So you might remember that, okay, this guy is moving and it has just one counter or something. Okay, and it just records the maximum position it has visited till that point. Okay, and once in a while it just resets to this maximum position. Okay, so it does unbiased random walk, and once in a while it just goes back to the whatever the current maximum at this point. So you can think of this one basically mixer of systematic search. So in the systematic search is basically you start from one point and then you just keep going in one direction. That's like a systematic search. But imagine that, okay, your searcher is not a perfect searcher, and what happens if it goes to some place, there is a certain probability that it didn't find the target, and then it goes to the next one, but then it's not going to come back to that place already visited, right, in a systematic search. So it's not going to find us, there's a certain probability it may not find the target again. So in this case, what happened, there's a tendency to go towards the maximum, but once in a while it also comes back to the previously visited sites. Right? I'm going to, so basically you think of it like a random walk. So till time n step, there's a maximum distance it has traveled, and it basically goes back to that distance. So let me just that particular point. So for example, it starts with 0. Let's say it goes to here. This is still the maximum. Yeah. So it's like, but in the more general case, you can just think of it like a periphery of the maximum this thing, and it just goes to one of the points in the periphery, basically. Yeah. So this one, in fact, you can just think of it like a, as I said, that this animals, they during foraging, you can just model it by a random walk. And for an intelligent animal like cow, for example, so you might imagine that they remember like the places which they have not visited or where they have not gone, and there's more likely to find grass on that side. So there is a tendency to go towards the periphery of the district because they know that if they go there, they will find more food. But again, they will come back and then go back to the district. For example, this guy is sitting there, right? So this is like a so you do something, and then basically once in a while you just go to the maximum periphery. It's in general in the D dimension, you just go to the boundary of the all the visited sites, and in the one dimension you can just think of it like a either maximum or the minimum of this thing. Okay. So these are the two problems I am going to discuss. One is the simple resetting to the origin, and the other one is just resetting to the maximum position. Okay. So let me just first talk about this diffusion with resetting to a fixed position. This is what Martin told, and let me just go through it once more. Okay. So this is your process. It starts with x0, and then it's doing some stochastic process, and once in a while it just reset to this point x0, and it happens with a constant rate, let's say r. Again, it starts from there, and this is your process. Okay. So what is the dynamics? So in a small time delta t, either it resets to x with a certain probability r times delta t, and with 1 minus r delta t, it just does diffusion. So this is the dynamics. It's a very simple dynamics, and you can write down the Fokker-Planck equation. This is the part coming from the diffusion part, and this is the one from the resetting, because this is, you can just think of it like a master equation. This is the loss term from position x, because it just goes from there, and this is the gain term at the position x equal to x0, because it comes from any position x to x0. Okay. So you can solve this exactly, and what you find is that this is your steady state distribution. Okay. So it's an exponential with a cusp at the resetting point, okay, where this is given by that. So as Martin has mentioned, this is a, although it looks like a equilibrium state, or you can just think of it like although it looks like some problem in a mod potential, but it's a non-equilibrium state because there is a current from all the points to this point x0. So it's a non-equilibrium stationary state. So the question I am going to ask, how does the system approach to this non-equilibrium stationary state in time? So what I am going to say that this approach is quite unusual. The relaxation to this stationary state is quite unusual. So before that, let me just say what do we mean by unusual. Let me just say what is the usual relaxation. So if you have some Fokker-Planck equation or master equation, if you have a steady state, so usual relaxation I would call it, so is p of xt goes like, okay, let's some p steady state of x plus some exponential relaxation to p1 of xt, which might also depend on initial point and something like that. So this is a usual relaxation. Of course, there are examples where this is not true. Like for example, I think David has studied, like if you look at the diffusion in a logarithmic potential, etc., this kind of relaxation doesn't happen. But what I am going to, I think even Ali had studied, so what I am going to show that it's not even that, it's basically quite different from this kind of relaxation in this case. Okay. So to study that, first I have to write down the time dependent solution. So what is the time dependent solution? So you can write down the exact time dependent solution using the renewal approach. So this is the propagator of finding the particle at x at time t with reset. So it has two parts. One is that coming from this rate trajectory which didn't have any reset up to that time. So this is the probability of not having any reset, exponential of minus RT times the free propagator, because there is no reset for this one. there's a part where you had at least one reset. Okay, so in that case, I can just look at the last reset, and this is the probability that there's a reset within a given amount of time d tau. So this because this happens with rate r, so r times d tau is the probability of a reset. Then this is the probability that there is no reset between this point and that point. So this is exponential of minus r times tau, and since during this time it moves freely, so it's given by the free propagator. So this is the exact time dependent solution for, in fact, for any reset thing with this kind of reset protocol. Okay. So for diffusion, you can just substitute this p0 is given by this, and you can easily find that for the stationary solution, when you take t going to infinity, this guy goes to 0 and it just comes from there. So this is, you can actually solve this, you can actually perform this integral exactly, and then you will find that whatever you have got that exponential solution, it will be easily given by that. So you can easily see that it's like a Laplace transform of this Gaussian propagator, basically. That's the exponential solution. Okay. So now let's look at the approach to this steady state. So we are interested in the large time behavior, because as here we don't care the full thing, basically what is the, how does it approach. So you can actually look at this one with the Gaussian propagator, and you can just write the same, this thing which has just a different form. Basically you just redefine this time tau by t, you can just redefine the variable, and this is the same exactly that, and where this phi is this function. So if you look this phi, how does this phi behave? So w is something, some variable which is bounded between 0 and 1. So as w goes to 0, this guy diverges like 1 over w, and when w goes to infinity, this guy again diverges like w. So there is a minima, single minima at this w star, and which is given by y by y star, this mod y by y star, because y can be both positive and negative. So now you have to solve this one. Now there can be two situations depending on whether this mod y is less than y star or greater than y star, because y is a variable which goes from 0 to infinity, right? So therefore there are two cases where this w star is less than 1 or w star is greater than 1. So if w star is less than 1, so for large time you can just find out the behavior of this using the saddle point calculation, and what you find is that saddle point is somewhere between 0 and 1. So the solution is just given by the saddle point. As you keep increasing y, at some point this saddle point hits 1, and after that saddle point goes outside the interval 0 to 1. But since your integral is from 0 to 1, what the contribution comes basically from this endpoint 1. So your solution is just given by this endpoint. So therefore you have a large deviation form where p of xt has this form exponential of minus t times x by t. So that's the one where this large deviation function is either given by this one, so phi at w star, which is given by this one, for mod y less than y star, and if this mod y is greater than y star, so this is given by this. And this phi, this large deviation function, is quite generically, actually you can show that there is a second order discontinuity at this point y equal to y star. So now if I just translate it to your p of xt, so what you see is that, so this is your space and this is your time. So there is a light cone, so within which you have a steady state solution. So p of xt is your that exponential solution within this light cone, so which is basically given by that. So there is some characteristic length which grows like t, and outside this light cone this solution is time dependent. Okay. So he said that basically at any time, you can look at any time, if you look at in the space, so there is a critical point in the space within which the solution is steady state, and outside that solution is a time dependent solution. And you can actually, so this is, you can just think of it like a dynamical phase transition, and basically just this line separates two kinds of trajectories. There is a trajectory which contributes to this non-equilibrium steady state, which are the trajectories which got lot of resetting between 0 and t, and there are some trajectories which got almost no resetting. So these are like the free trajectories or very few resetting. Okay, so there is a steady state in between, and there is a transient, and you can see basically the solution. You can just write it as a within one non-equilibrium, and outside is a transient solution.
So what I'm trying to say is that for any fixed time, no matter how large it is, there is a sufficiently large value of x, so that beyond this value of x, this is still dynamic.
Exactly. Yeah. So either you can fix your time. Either you can fix your time, and then you see that there will be some x where it's dynamics, or you can fix your x, you sit there, and you see that after some time that in that position your solution becomes steady state basically. So it's a transition from a transient state to a steady state basically. So that's why you call it a dynamical transition. Okay. So so this is actually you can just verify it. So for example, if we just do it for a diffusion, this line is the exponential line, and you see that so initially it follows the exponential 1, and at some point it just goes to the other solution, and this dashed line is the time dependent critical point basically where your solution goes from the one solution to the other solution. Or you can also look at in this variable x by t, and then you see that basically this is your full thing, and it's described by the large division form quite well. Okay. So in fact it's quite generic, so although I have talked about the diffusion case. So in many of these problems your free propagator has this scaling form. I mean, many of the stochastic problem we know the free propagator has this scaling form. For example, if you have a diffusion, then this h is your position, and this beta is half, and this g of x is a Gaussian. If you have a fractional Brownian motion, h is again a position, beta is your Hurst exponent, and g of x is Gaussian. If you have a Edward-Wilkinson interface, then this h is your height, and beta is 1/4, and g of x is again a Gaussian. If you have a KPG interface, h is your relative height, beta is 1/3, g of x is residuum distribution. So this form is for many systems is a generic form, and what we see actually many of the systems, this g of x has this stress exponential behavior. Of course, there are cases where g of x, I mean this can have a power law thing, but we are excluding those. And so what actually enters in your saddle point calculation is basically your this tail of this g of x. For example, this for diffusion, these guys are given by this. For KPG, these are given by that. So this is a quite generic listing, and so you can actually carry out this whatever the thing we have done before for generic case, and you see that there is a generic large deviation form, and there is a inner core where your steady solution is stationary, and there is a outside region of the inner core where the solution is transient, and there is a generic second order discontinuity at those singular points basically. Okay.
Sorry to interrupt you, but for the KPZ this is not the whole story. I mean, there is with time, there is this cone like you showed, and within it the solution is stationary essentially statistically. Then there is this dynamics that is described by the traceability distribution. But then, still further, there is a crossover to another regime which has a different large deviation scale.
No. What I'm saying is that so suppose you just look at the Okay, so suppose you look at the KPG with a on the infinite line,
yes.
Right? So what I'm saying is that so KPG with resetting, you're looking at it.
Oh, okay. I didn't catch.
Yeah.
Okay.
So the resetting is still there. So you have this.
What is resetting?
So resetting is basically goes to the flat interface. Suppose KPG with a flat initial condition.
And you bring it back to flat.
Flat initial condition. Yeah. So whatever your underlying stochastic process, basically you bring it back to your initial condition with certain rate. Okay. And then, so this is a general expression, and you can see that again. Okay, so there is an inner core and then the outside one. So in the inner core there is a steady state, and then outside one basically there is a transient state. And generically, basically there is a second order discontinuity at this point. So this is some simulation of KPG, TASEP basically, which belongs to the same KPG family, and you can actually see that it matches with our prediction. Okay. So generic picture is that basically the P of xt which reset, has this large deviation form. So where it goes like exponential of minus some rate function x divided by some time dependent length scale, and this time dependent length scale can be different for the right and the left side. For example, in KPZ it's not symmetric, but so what we have is basically there is an inner core and there is some length scale, and within the inner core you have a non-equilibrium steady state, and outside the inner core, outside the core region, you have a steady transient state. And this transition along this is a second order transition, dynamical transition. So let me just repeat it. So if I just sitting at a fixed position, so what happens that initially my state is transient, and at some point the state goes from the transient to the stationary state. Or if I am at a fixed time, then what I see is that basically there is a region in space where your solution is stationary, and the outside the region your solution is transient.
Sorry, I need to ask this again.
Yeah.
Again, for the case of the KPZ, what did you assume about the reset rate compared to the intrinsic nonlinear time of the KPZ equation, the time when the weak coupling crosses over to the strong coupling? Now, there is a typical KPZ time which you can put together using the material coefficients and the diffusion coefficient.
Yeah, lambda. You
New
see.
lambda and d, there is a typical time scale. So your reset time scale is much shorter than this one or much longer than this one?
So this is basically the, I think that so if you look at for the so what happened actually is, so this is when you look at the, so when we look at the large time behavior, so because we look at the steady to the large time whatever the relaxation to the steady state. So in that case, when you look at a large time behavior in the scaling regime, what is important is your Tracy-Widom distribution, basically. Tracy-Widom distribution.
So assuming R is much bigger than the
Yeah, exactly.
R is much bigger, so the reset time is much shorter than.
Yeah, exactly. Yeah, exactly. Yeah.
But to be honest, actually, when we did this computation, we didn't really have in mind, proper.
Yeah.
What I'm trying to say is that no matter what time is, even for very short times, the far tails are very different.
Yeah,
You know nothing about the Tracy-Widom yet.
Yeah.
This must somehow come into play, right?
This regime we have not really.
Yeah, exactly. Yeah. Okay, so this is a generic picture. So let me just go back to the next problem. I have I think some 10 minutes about, or 15 minutes. I have, okay. So let me just go to the next problem, which is the resetting to the maximum. So in the previous one, I have been resetting to the initial condition, and I was looking at this how does the system approach the steady state. Okay. So let's go with the next problem. So this is the let me just define the model now. So this is my x coordinate. So this is random walk in now discrete time, discrete space. Okay. So xn denotes the position of the walker at step n, and mn is the maximum of the all the mn is the maximum, current maximum at that point, basically. So for example, at nth, so it has visited the point x0, x1, x2 up to xn, and mn is the maximum of all those points. Okay. So what is the dynamics? So dynamics is in the x. So what it does, so it starts with the maximum, because when you start with the initial point, that's your whatever the definition, by definition that's your also maximum. And now with probability half it goes to left and probability half it goes to right. When it goes to right with probability half, your maximum also changes by 1. Right. So this is the axis for the maximum, and at some point this will be in the interior, and when it's in the interior, so what it does with a probability 1 minus r by 2 it goes to left, 1 minus r by 2 it goes to right, and with a probability r it goes to the maximum value. So in that case maximum doesn't change because it has gone back to the old maximum. So this is the dynamics. Okay. And now the question is, under this dynamics, what happened to x or what happened to m of n? Okay. So in fact actually there is a nicer way to do some kind of rotation. What you do is you plot this maximum along this axis, and this axis, instead of the position, you just look at the position from the current maximum. So then actually you have this nice comb structure, and maximum is greater than 0 because you always start from the 0. And this y is by definition is a positive quantity, so you have these infinite lines, and your dynamics is this. So dynamics is that basically whenever you are on the any of these lines, with 1 minus r by 2 you go up, 1 minus r by 2 you go down, and with a probability r you go to the 0. And once you are on this line, with probability half you go up, with probability half you go right. You cannot go left basically. That's your dynamics. And you can actually write down the generating function for this equation, and okay, we can actually solve this thing, but I am not going to give you the how you solve it. It's quite involved, and you can actually look at the paper. But let me just remind you what happens to this problem if there is no resetting to the maximum. So it's just a general normal random walk, right? So in that case, you know that x is just a diffusive for a large n. So for large n, it's given by this one, and also the maximum is a diffusive. Maximum is one-sided, but it's also diffusive, this thing. So both x and m, it is a diffusive growth without any resetting. Now you want to ask what happens if you put this put a non-zero resetting probability r, which is between 0 and 1. Okay. So what we find is that your maximum, so which goes like square root of n for r equal to 0 without reset. The moment you make it reset, it actually grows ballistically. So there is a velocity with which the maximum grows, and the same thing is for x of n, the position. So position mean is of course 0 now because it's a this thing, but for r equal to 0. But the moment you put non-zero r, there is again a finite velocity, and it goes like that. And what is interesting, that this velocity which appears here is the same velocity which appears here. So both maximum and the position, they move with the same velocity. So as if the position is basically latching onto the maximum. Okay. You can also look at the fluctuation. So about this mean velocity, and this variance is basically given by, so it has this diffusive this thing. So this diffusion coefficient, which is for r equal to 0, you can actually compute exactly, which is 1 minus 2 over pi. But the moment you put a non-zero resetting, it becomes something very different. Okay. The same thing is for the fluctuation for the position, and this diffusion coefficient is again the same diffusion coefficient which appears in the maximum. So it's basically maximum and the position, they behave almost the same way. Okay. And what you see is that if you take this r going to 0 limit of this diffusion coefficient, that's not same as r equal to 0 case. So if you take this d of r result and take the r going to 0 limit, that's different from r equal to 0 case. So this r equal to 0 case is a singular point, so which is different from the general r and taking r going to 0. Okay. Let me just give you the expression of this velocity and this diffusion coefficient, and which you can actually compute exactly. And the velocity as r goes to 0, it vanishes as square root of r, and the diffusion coefficient as r goes to 0, which goes to half, which is different from your r equal to 0 case. For if you remember r equal to 0 case, for the maximum the diffusion coefficient was this one, and for the position diffusion coefficient was 1. So this is very different. So
why in the r equal 1 you don't get d of r? R equal 1 means that you always go to the maximum. So where you start, then you should remain there. So the velocity should be 0.
No, because if you look at the, let's look at the dynamics. So if you put r equal to 1, so it will be maximum, but once in a while you can basically come back to the previous point. So it's just near the maximum, because once you enter maximum, your dynamics is slightly different. So you basically with a probability half you go left, and with probability half you go right.
You start at 0, that is your maximum, and with probability 1 you stay there.
No, as you see that if you are already at the maximum, your dynamics is different from the dynamics in the bulk. If you are inside, if you put r equal to 1, basically there is no dynamic because you don't go there. But if you are at the maximum, their dynamics is different. It doesn't involve the resetting. If you are at the maximum, you with a probability half you go to the left, and with a probability half you go to right. So what happens if you are at the maximum? So with probability half you basically keep going to this. So it's you are very close to the maximum, but so you are there. With probability half you go up, but with probability half you go to back, but then immediately you next step you go to the maximum again. So r equal to 1 is basically you are just at the maximum or near the maximum basically. Did I answer your question or no? Yeah. Okay. So now the question is, as you see that there is a different behavior for r equal to 0 and r going to 0 limit. And the question is, can we interpolate between this r equal to 0 and r going to 0 behavior? Okay. So it turns out that actually one can interpolate between these two by a crossover function, and what you can do, like for example the average maximum, you can write down this scaling form. So where it goes like square root of n times some scaling function of r times n. So this is in the regime where r goes to 0, n goes to infinity, keeping this product r and n fixed. And similarly you have a scaling relation for variance, and this scaling function you can actually compute exactly, and you see that is a quite non-trivial scaling function, right? And now you can just look at these two limits. For example, r equal to 0 means this y going to 0 limit of this scaling function, and if you take this y going to 0 limit, so it behaves like that. So at y equal to 0, this is square root of 2 by pi, and if you remember, that answer was square root of 2 by pi times square root of n. On the other hand, if r equal to 1, because you have taken n going to infinite limit, so basically r equal to 1 limit is correspond to the y goes to infinity limit of this behavior, and you see that at this point your behavior is given by this one. So this is basically okay, y going to infinity, this is your leading behavior. That that square root of y, that cancels with so that gives you your old behavior, because if you remember this was going ballistically, so there is a square root there and there is a square root here, and that makes it linear basically. Okay. Similarly, you have a scaling function for this thing. So this gives you the r equal to 0 case, and this gives you the r equal to 1 case. So it just nicely interpolates between these two. Similarly, you can do it for the position. Again, you have the scaling functions, and you can which interpolates between r equal to 0 case and r equal to 1 case nicely. But this is like a non-trivial scaling function which you can compute exactly. Okay, this is similarly for the variance. Okay. So now the question is, okay, since the maximum and the position both behaves more or less similar, so they latches onto each other. So this is, if you look at this variable, how does this variable behave? There is still fluctuation. It's not that they are on top of each other, right? So how does this variable behave? So since they are very close to each other, you might expect that there is a steady state for this guy, and indeed there is a steady state behavior for this variable. And so what you see is that, okay, steady state means in the sense, okay, it again has this large deviation form. This y is the distance from the maximum, which has this large deviation form, and again it has these two regimes when there is an inner regime where there is a steady state because it's linear in w. So when you write there is a n, so that n cancels. So there is a stationary state in the inner regime, and there is an outer regime which is a transient time dependent distinct. So again you have this similar dynamical transition for the this position difference from the maximum basically with respect to maximum. Okay. So conclusion. So for a stochastic process, if you look at a stochastic process which doesn't have a stationary state, so resetting basically leads to a stationary state. This was shown by Martin Evans and Saitya Majumdar, and they have a couple of papers. But what I have talked about here is that the relaxation to this stationary state is quite unusual. So it's an unusual this thing, accompanied by a second order dynamical phase transition. So there is a core region where you have a non-equilibrium stationary state, and outside this there is a transient state. And in other words, if you are basically at a fixed position in space, so there is a time before which your state is transient, and then it dynamically goes to a non-equilibrium stationary state. So I have also talked about the resetting to the maximum, so that leads to a ballistic growth for the position and the maximum. They have the common velocity, they move with the same velocity, there is the same diffusion coefficient. And again, there are probability distribution of this difference between the maximum and the position. So it again has this similar dynamical transition. Okay. So there are a lot of other aspects of this resetting problem. I just picked up 2 things. And for example, there is target search problem, which I didn't talk about. Martin has talked something like that. And for example, you can also look at a target search by a Levy flight instead of a diffusion, and this is what we looked at it in this paper. And then you see, actually there also you see this interesting some kind of transition, phase transition. You can look at a continuous time random walk with resetting, diffusion in a confining potential. For example, Agranov has looked at it with resetting, fluctuating interface. Again, you can resetting. What here I have talked about the relaxation, but you can again look at what is the steady state, and these people have studied there. There are different other processes with resetting. Okay, then there's stochastic thermodynamics with resetting, and then there are other things. Okay, there's this talk by Martin, which you have already heard. There's another talk, I think, tomorrow or something. And I think Agranov has a poster here on this thing. So, okay. Yeah, thank you for your attention. Yeah.
So, thank you, Gregory and David, for the nice invitation. And so I'm going to talk about a particular kind of adaptive random walk and their localization properties. So in this talk, we are mainly interested in non-Markovian processes and a particular kind of non-Markovian processes, which is driven by a reinforced dynamic, which loosely speaking can be defined as history-dependent processes or path-dependent processes, where past states or transitions between these states are more likely to occur again. So this is so you have some time-dependent transition rates, but which depend on the trajectory of the process itself. And the interesting property that of this work that is that it can give rise to adaptive behavior. That would mean by adaptive that the states may fit some environmental conditions or some imposed external conditions, which maybe would not be observed in a simple random walks. So in the model, so the main property emerge because of recurrent visits to same states or place, and in principle it's maybe not enough, apart from the time that, for instance, first passage time property may be difficult to calculate. They may not give a full picture or full understanding of what's going on in this kind of process. And there have been many applications, in part naturally in biology. For instance, there are the classical example in ant or bacteria colonies that, thanks to reinforcement, are able to fulfill some particular biological functions. So there is this classical experiment where you have a nest and a food source, and you have a long path and a short path. So that's an experiment. After 4 minutes, the ants are a little bit everywhere here, and after 8 minutes, they start to only select the short path. And the thing is that they leave pheromone on the path, and pheromone attracts, each ant attracts through the pheromone trail other ants. So the ants that randomly choose the short path to go and to come back to the nest are the first one to come back to the nest, and the new ants that may come out will be a little bit more likely to follow this higher concentration of pheromone. And it's kind of an autocatalytic process, which which rapidly sets all the colony, nearly all the colony to follow these. And maybe this system is not very flexible, because if we start only with a long path and after some time add a short path, maybe a few fraction of ants realize that there is a shorter path, And so there is in ecology, so it's important to, in this case, it's an example of adaptation to the environment. So you have a routine, you have preferred route or preferred place, the way you come back frequently without ignoring other part of the phase space. But there is an important trade-off between exploitation, which is this nearly deterministic dynamics, and exploration, search, in order to find out what are the optimal solutions. So in a colony, mathematically speaking, each diffusing element interact with a field created by others. So you have kind of a mean field limit. So it's possible to write down some Fokker-Plake equations, for instance, for the density of entities and the density of chemical scents, which are local in time, although they are non-linear. And here we are especially interested with a single individual interacting with his own trajectory, where fluctuation cannot be really neglected. And so we may ask, what are the recurrence properties, the kind of transition between these recurrence properties depending on the parameters, and the possibility of localization transition, which is basically when just the random walk does not stops to diffuse altogether. Of course, this single individual has application to individual animal movement and the study of human mobility, which is driven by memory and reinforcement process. And so especially the use of spatial memory can lead to emergent pattern that can decrease the average processing time or provide a better adaptation to to an environment. And maybe they can be used in computer science also as for solving a complex optimization problem. So in the typical ordinary random walk, you have transition rates which are constant for the symmetric case between neighboring sites. In reinforced random walk, typically these transition rates, for instance, can depend either on the number of crossing, that the number of times where a given edge has been crossed, or the number of times a given site has been crossed. So they are edge reinforced and site reinforced models. And the simplest model is, for instance, where you have this function which is 1, as in the usual case, when the site has, or the edge has never been visited before, and 1 plus a when the edge has been visited at least once. So this is a single time reinforcement model. This is a linear reinforcement model where simply we have a linear relationship between the rate at which a site, for instance, is visited and the number of visits that this site has received so far. And there are very few rigorous results shown for this. Maybe one of the most famous one is the case of the one-dimensional lattice with nearest neighbor hopping, where the function fn grows faster than linear with n. And in this case, you have a severe localization where the walk becomes trapped between a single edge or two sites that are visited asymptotically very exclusively with probability close to 1 or 1. So here these are, for instance, even in the simple case of the single time reinforced walk, varying this parameter a can give rise to very different behavior. Like for small a, typically something which resembles a normal random walk, to this case of a equals to 3, something which is much more circular in the order at which the sites are reinforced. So these trajectories look basically as a random walk which bumps into a balloon which is growing over time. And so
what is this pseudo-Arrhenius conjecture?
So yes, it's that there is a critical, there is a critical A here in such that you would have typically a change in the fractal dimension of the contour of the random walk. So going from something which is typical of random walk and extremely fractal to something which is very regular and of dimension 1, basically. Reinforced process are also very important in learning. So it's a mechanism by which we can learn, or agents can learn things. And this is a little bit the case, like for instance in the short path and the long path for the ants. They kind of learn without global knowledge that there is a short path that will only exclusively use. So learning is usually defined as a change of behavior which is induced by the experience. And so in a non-spatial context, for instance, we can play games in the kind where you have some box, you have some options which are heterogeneous. So you have each option gives you a value, vi, so which is quench, which is fixed. And initially you don't know where is the maximum value, right? So there's random numbers. And you choose randomly a box and you update the gain from box I by adding the value of the box that you picked to the gain that you had so far with this box. And the probability to choose a given box is proportional to the gain that you have received from that box. So after repeating this process many times, so at large time, the activity concentrates on the place that has, on the box that has a maximum fitness or the maximum V, with probability close to 1. So there are some evidence that in foraging animals, single foraging animals, there is a learning process taking place. So this is a seabird, and there is a comparison between adult individual and a young individual. So here are some data. So this is a very long period. So each second is about 2 minutes. So, 10 hours period. This is a nest where they come out. And so these adult individuals go out and typically concentrate their activities on some particular zone in the sea. And they come back, like a little bit similar to a resetting process, to their home, their nest and their central place. And this is what the young typically are doing. So here we see some kind of localization or some kind of restricted foraging zone. And the young individuals are kind of more random in their movements and more exploratory and don't know very much where to go. They finally come back after some long trip. So here you have some kind of activity region which seems to be rich in fish, probably. But for instance, here this zone is not much explored, whereas the older individual come back. And it's not because they have more energy or they are fitter. Actually, they have smaller body size. They are less resistant than the adult one. So they should not be doing this if they were really optimal. And actually, this shows that this takes place not on a completely uniform landscape, but which is quite structured and relatively complex. Which is driven essentially by currents, oceanic currents. So okay, so I don't know if it's working. These zones actually correspond to particular zone regarding some Lagrangian structure that are in the ocean, and they are correlated to the fish density. So these are data, so it's a 2-minute resolution, and each second is a couple of hours. So this is a landscape, so that these individuals actually don't go anywhere on the sea, but they go to some particular places and come back from there and exploit these resources. So of course, the information gathering that this implies over time And the use of memory that these birds do is valuable if the environment doesn't change too much or too fast and is sufficiently heterogeneous so that you may have some better choice and not so good choice. Another example where memory is supposed to be important is during the home range formation of animals. So this is example of capuchin monkeys, which have been mentioned in previous talks. This is this blue is a 1 month trajectory in this island, which is in Panama, which is only 5 kilometers wide. And so it is as if this system will be confined in a very small region of space without any physical boundary, which are really visible. And for instance, an example of maybe indirect signature of the complex trajectory, maybe the use of memory in this system, is if one plots the probability that a randomly visited site, so you discretized this plane, has been visited exactly m times during the time period, is broadly distributed. So there are a few sites. So this is the green data here are these capuchin monkey. So there are few sites that have been visited about 100 times, and most of the sites have been visited only 1, 2, or 3 times. So there is a wide diversity in the visits, whereas a random walker, a 2D random walker, for instance, would be given by a much sharper distribution here. So there are some kind of recurrence property which are not very common in usual random, that are uncommon for a random process. And this is actually the prediction of a model that we've studied and that was mentioned earlier about resetting to a preferential visited place. And I come back later. So we would like to study reinforced random walk when this value of these sites are actually spatially distributed on a lattice, and you have a random walker that can go from one place to the other with this impurity. And the central question here is, can memory random walk with some rules, for reinforcement rules, can be useful to learn something about this environment? And can it be advantageous? So it would be a successful adaptation, for instance, concentration around the rich sites. And we were trying to look for an analytic model, and which is actually the one that I want to present here, which is a solvable model, a partially solvable model of spatial learning that we have studied recently with students of mine, Andrea Falcon-Cortez and Luca and Satya. And so essentially we consider a lattice in discrete time, a discrete space, and there are 3 phases: a phase of exploration, also random motion, a phase of memory, and a phase of feeding, if you want, or exploitation of resources. Essentially, with probability 1 minus q, q is a parameter, take a random step drawn from a distribution, so for instance, nearest neighbor distribution, symmetric. Memory phase that with probability q, which is kind of a resetting rate, the individual relocate directly to a site visited in the past. So these are these blue site which has been visited previously, this black site which has never been visited, and the current location. And the probability of choosing site I, it was mentioned in the talk by Martin and Sanjib, is in this case proportional to the time spent at that site since the beginning of the process at time 0. So it's a reinforced process which is modeled by these relocation events. So which is inspired from the model of Martin and Satya, in which the reset took place to the fixed site. So here with the resetting place, the resetting point is a stochastic variable, but highly visited places are likely to receive more visits. And there is, for instance, there might be some impurity, like this red site here, which is special. So this is where food is, for instance. So with probability gamma, there is a second parameter. You stay to that site at the next time step. So you have a trapping time, you have the waiting time on that site. And with a 1 minus gamma probability, you do one of these two rules with their respective probability. So the idea is, since you're staying a little bit longer here, so everything is, these are sites with waiting time is equal to 1, and here you stay a little bit longer whenever you arrive at that site, because it's more important site. We'd like to see how this can affect the dynamic of this system. And okay, so if we write down the master equation, so this is a probability to be at site n at time t plus 1, starting from, for instance, site 0, or it doesn't matter. So there is a standard diffusion part, and there is a memory, two terms which are non-local in times, which involves the resetting parameter q, and which counts simply the number of times. So to get to n, you just count the average number of times you were to that site between 0 and between times t equals 0 and t equals to t, t prime is equals to t. And this is a normalization factor, basically. So this is equivalent. So you choose a time at random uniformly between 0 and present time, and you reset to the time, to the place where you were at that time t prime. So it's equivalent to a preferential, linear preferential visit model or reinforced model, because if you have visited a time very often, a site very often, so there will be many times where this corresponds to that site. And if you have only visited once a site, so it's very unlikely that you pick just the time where you were at that time. So this is a reinforced dynamics. So we have infinite memory in this case, because it's a flat memory kernel. So this memory kernel K mentioned by Martin is just 1 over t in this case, or 1 over t plus 1. And we have an inhomogeneous medium. And so it seems to be like an unnecessary complicated problem to study. And in addition to that, there is another consequence of the inhomogeneity, is that the resetting probability, or the resetting rate, is actually position dependent in that problem. And that's a key element, key ingredient for having actually localization and learning in this problem. And this can be seen because it depends, if when you reset to site n, it depends whether at the time just before that you are on the resource site here, or you are on another site. Because if you are on the other side, this happens with probability q, and on the other case, it would be decreased resetting probability, because you will stay more likely on this site. So so this complication here, the last complication disappears when gamma equals to 0. So not only we don't have any inhomogeneities here, but this problem only involves the single time probability of presence, Pn of t, so in a closed form. And this problem is solvable, because this problem is not solvable exactly in principle, because we have a single time probability with a joint, depending on the joint probability distribution, which in principle cannot be factorized. And so you would have a full hierarchy of equation with an infinite number of probability distribution. But if gamma equals to 0, this does not happen. And that was actually the case that was studied in previously, the first one that we considered a few years ago. And it is exactly solvable. And we can write down an expression for, in the case of nearest neighbor jumps in the random phase, for the mean square displacement. that takes that expression, which actually is very similar to the problem, to the expression obtained for the record statistics by Satya yesterday. Actually, it's exactly the same. So you have exactly the same reason for the mean square displacement, which goes logarithm, which is proportional to the logarithm of time at large time. So it's extremely slow dynamics, ultra slow diffusion, and it is possible to show also that the distribution slowly converges to a Gaussian distribution with that variance not given by the usual dependence linear in time, but with this logarithm of time. And so at the end of, so after astronomic number of steps, probably the process will slowly converge towards a Gaussian. So this model without any impurity, so gamma equal 0, and describe relatively well the diffusion of monkeys in their environment. So these are these green lines, and the model. So this is for the time average mean square displacement. This is ensemble average mean square displacement, and we can more or less so fitting this curve, we can calculate the number of the distinct visited sites. And so which also fit, so without any additional tuning, fits the observation relatively well. And we can actually estimate a resetting rate for this system. So it is relatively low use of memory, but that's a value that best describes these curves. So it looks really small to 4 to the minus 3, so it looks really negligible, but after a few hours, this strongly affects the dynamics of the system compare, and you can see here the curve of the normal diffusion with Q equals to 0. So Q equals to 0, in this case is a simple random walk. So here we have so we consider now gamma different from 0. So we have the starting point. Here you have the impurity, so it changes the color the first time it is hit by the walker, but the rules are just updated continuously. And what we can see is some kind of localization around that resource site. So, and actually there is no longer diffusion, like logarithmic diffusion, as in the previous case. So that's what can be quantified here. If you record in the simulation the number of visits to the origin, so which is this green curve, and the number of visits, cumulative visits to the impurity, so which is characterized by the strength gamma, which is this blue curve. So initially the origin is the most visited site, but starting from the time where the impurity is hit for the first time, it is very quickly reinforced, and then it starts to receive steadily number of visits, and it is visited all over the time at a steady pace. So and the density. So this is a trajectory typical at large value of the resetting rate. If we decrease the value of the resetting rate, maybe that state can be lost, and we have more diffusive trajectory, although it's logarithmically slow diffusion, right? So this is so this suggests that maybe we have phase transition between diffusive states or non-localized states and non-equilibrium steady states that emerge in this system. So we can define P naught. So by looking at histograms of the asymptotic probability of presence, one finds typical these two by exponential typical of problems with resetting, where P naught here is probability of presence at the resource site, and we have a typical characteristic size for this distribution. And as the memory parameter is varied, we see that the P0 becomes stronger and stronger, or the other way around, that it is decreased. At some points, it goes to 0. And these are simulations that suggest actually, so this is a theoretical curve, and the simulation as the time is increased suggests that we have a kind of second order phase transition between a localized phase and a delocalized phase.
What is
P0 is that quantity. It's the maximum of the probability of presence. Right? And so if you increase the strength of the impurity, so it's a more important, it's a richer site, so you move this curve toward a 0 value of Q. So we can do an approximate, we can have an approximate solution of that problem analytically. First, using a temporal decorrelation approximation. So this troublesome term which has a joint probability distribution, we just say that is a product of two probability. So this is the first great simplification. And the second is we directly take the limit t infinity. So nothing dependent on time, and we kind of look directly an attractor of the dynamics. And this is very easy to solve. So there is a trivial solution where there is p is equals to 0 everywhere, and a solution which is given by this, so we're in Fourier space. So here, this is a Fourier transform of the distribution of the random steps, of the random underlying process, and this is this P0, which is a constant yet to be determined, and these are the parameters of the model. And P0 can be obtained self-consistently by inverting back this expression, evaluating it at the site, at the origin where the resources is located, and we get an expression for P0 as a function of the memory parameter or resetting rate, which is here, here, and here, the strength of the impurity, and this is the variable so the P0 is obtained by solving this equation. And it's easy to see that this equation has a solution only if Q is larger than a critical value, which is simply given by this, and by this 1 over gamma, and which in times this P no return, which is a classical no return probability of random walks on lattice, Markovian random walk on a lattice, which is given by this expression. So it involves the Fourier transform of the random step distribution of the underlying random process in between resetting events. So, which means that since 1 minus p of k is proportional to k to the square, in dimension 1 and 2, this integral is infinite. So the inverse of the integral is 0, which means that here you have 0. So this is a recurrence property of the random walk, well-known recurrent. So all the random walks in dimension 1 and 2 are recurrent, and p no return is 0, or p escape is 1. And QC is then equals to 0, which means that localized solution always exists in that case. And so in dimension larger than 2, on the contrary, QC P no return is finite, and there is a finite critical value of this resetting rate. So the message is that important properties of this complicated memory-dependent process depend on the simple random walk property, is a Markovian random walk on a lattice, at least for for this expression. And so if this is given by Levy distribution as small k, it's we have this is given by k to the mu. And in this case, the critical dimension is equal to mu. So if you take mu equals to 1/2, for instance, which is what we took here in 1D, we have a phase transition at a finite value of QC. And so for the nearest neighbor random walk in 1D are always localized, and we can calculate in a simple form, can be obtained for P0. And we can see that actually the decorrelation approximation that we did seems to be to work very well for this case. Here we can see some differences. Probably they are due to the transients that are very, very slow, because all the dynamic is logarithmically slow in this kind of problem. So this is a phase diagram for Levy flight. So simply by plotting this expression in a plane, so we can identify a region where the structure is localized on the heterogeneity, and from a phase where it is delocalized. So if you don't have enough memory, or don't use memory enough below a critical QC, you are kind of the delocalized regime asymptotically. Or if the resource site is not interesting enough, so you don't fix it, you're not fixed on this site. So there is an interesting property. So if you remember in the previous talks, some much attention has been paid to this equation for the resetting to the origin. And in Fourier space, the stationary state of that solution of that problem has this form, where Q star is replaced by R, in this notation, in the resetting rate. And we find actually the same expression in this problem. So this Q star can be interpreted as an effective resetting rate, which depends on the true resetting rate in this problem with memory, the gamma, so the impurity strength, and that quantity P0. And so since P0 goes to zero, reach zero at the critical point, that means that the effective resetting rate vanishes, so the non-equilibrium steady state disappears at criticality. And one can form a characteristic length, Xi, which is the localization length, or the characteristic length of the steady non-equilibrium steady state. And it is easy to see that this Xi diverges algebraically with near QC, which is typical of a second order phase transition. And the exponent nu can be calculated as a function of dimension. And for the case of Levy flight, so here we have Q square will be replaced by Q to the mu. And so it doesn't really make sense to talk about localization length, so characteristic length. But we can still compute this exponent beta for the transition. So these critical exponents actually are identical in another very, very, very different context to the critical exponent found in the self-consistent theory of Anderson localization. And the reason is that in that theory we have a self-consistent equation for the diffusion coefficient of waves propagating in disordered media, which has a very similar shape to the one that we had for that quantity P0. And so here we can see essentially that the localization happens when omega goes to 0 limits. So if, for instance, we are in dimension 1 or 2, and we make this to 0, the integral diverge, right? So, so when we take the limit omega goes to 0 of that quantity, that must be finite in 1D and 2D, which means that d omega must tend to be like proportional to omega. That means that it tends to 0. So which means that in 1D, in 2D, we have localization in the Anderson problem, where here eta is the strength of the disorder and D is the dimension. So and in dimension 3, where this divergence does not exist, or we can put to 0 this, so there is a diffusion coefficient that vanishes at the finite disorder strength. So in our problem, in the case of Levy flights, we can show that that they are localized with a power law profile, not an exponential profile, but which is very similar to what found with stochastic resetting to the origin, the stochastic resetting to the origin of Levy flights. So I just conclude with a variant of the model. So I stressed at some point that the important, the non-trivial properties in this, and the existence of this transition is really dependent on the fact that, so we have memory and reinforced motion to highly visited sites, but this leads to normally slow logarithmic diffusion. We can suppress this diffusion by putting some impurity or some resources. But we can also consider a variance of the problem where all the sites have a waiting time of 1. And here we have a site-dependent resetting rate. So we have a site, for instance, where the walker does not reset. So every walker will be here, we jump with probability 1 to one of these two sites. So these two sites will be reinforced indirectly. And from these two sites, they can come back to that site. And so that mechanism actually allows the existence of non-diffusive, non-equilibrium steady states, which and the quantity P0 is given by this. So in this type of problem, so we say that it's learning because the resetting, so it's very similar to stochastic resetting to the origin, but we do not tell where the walker should reset. So the walker just find out by diffusing and just by reinforcing certain position where to reset. So it's a kind of an emergent process, but the shape of the probability distribution is very similar to the stochastic resetting to the origin. And in this case, the shape P0 varies in a non-monotonic way with the resetting rate. So I will stop here and skip some other problems that we can, for instance, so I can just let this animation, which consider a swarm of memory random walkers. So initially, there are many target sites now, and so there are walkers, and initially there is a resource site which is the maximum of it. So you have a uniform distribution of parameters gamma or impurity strengths, and very rapidly, relatively rapidly, the swarm is able to concentrate around this impurity site and ignoring the rest. So maybe this kind of property could be useful, for instance, to solve optimization, to be used as an algorithm to solve a complicated optimization problem. And so that's more or less what I wanted to say. Thank you very much.
Mm-hmm. But this eta, okay, I forgot what is eta in the random walk model.
Yes, or okay, in the random walk model, so you mean this eta, right?
Yes,
yeah, this gamma.
Later on, when you have this connection to Anderson localization, you do the analysis.
Okay.
So the omega goes to 0, and then equals 3, you have a transition, right? Which is
yeah, there is a factor. You mean this one?
Exactly, yeah.
Yeah, so this is a model. This is different parameters. This is these are the which is related to the distribution of energies in the on-site energy on the Anderson model. So you have the width, you have some fluctuation. It's and this is typical. This is a square root of the variance of that fluctuation of that distribution of energy is that parameter eta typically. And in the random walk model, yeah, it's yeah, well, it's exactly the same exponent, the same transition. So here, yes, there is a eta here, which is quite analogous to the gamma of the model, but we have an additional parameter which is q, and tell me also that can be taken as the parameter as well.
We thank you again.
Okay, thank you.